Today, sir, we have 4 sessions.
মাস্ট না কি আমি প্যানেলিস্ট আমার কোশ্চেন তুমি শুনলাম কোশ্চেন টোশ্চেন করতে হবে
Morning.
Morning, Soumitra. I'm sorry. I'm going to replace you for the first one because 11 o'clock I have to join the engineers conclave of IT.
Right, yes. Anyway, today is a Sunday, so no issue.
Yeah, but Parthu made me study what is remanufacturing right in the morning.
Most of us are.
And for me too, not maybe this morning, but 1 month back.
Right.
Actually given me an opportunity to understand a bit of it.
Can we start? Yes. Dr. Manna is having a meeting at 11. Yes. So good morning. Although right now we have 27 participants, but I believe it will increase quite soon. But Dr. Manna is having a engagement from 11 o'clock. So we should start right now. I welcome Professor Indranil Manna in this international workshop organized by National Institute of Advanced Manufacturing Technology and Futuristic and Advanced Manufacturing Forum of India. Little we understood in a very short period of time, particularly during the last 4 sessions about remanufacturing. It is quite evident that surface engineering, particularly across the length scale, is going to play a key role in the success of application of remanufacturing. So, given that, we have Dr. Manna to speak on application potential of surface engineering, and I identified right now all the 4 speakers in this session are alumni of BE College, and that is, I mean, not intended. By default, it happened. So, thank you all. I will request to introduce Dr. Manna.
So can that be spared so that I get 2 more minutes at least for me?
Yeah, I believe it is logical because Dr. Manna really do not need an introduction, particularly in our country and abroad. So yeah, you are free to start.
So I'll do the introduction myself. So one has to just confirm whether the slide is visible.
Yeah, absolutely. But
visible.
You need to make it full. You need to make it full screen.
Now it's full screen.
Yeah.
Okay, good. I think at the outset, I must thank not only the director, but the organizers of this particular conference from NIAMT. I still tend to always refer to as NIFT, but it's now NIAMT. First and foremost, let's understand where we stand today. The contribution to the GDP of India, which is again over $3 trillion US, is not even 20%. I mean, in some quarters, I see reports of 22%. I'm not sure whether that's correct figure. So my understanding is it's anywhere around 18–19%. At the time of independence, 1947, India's contribution from manufacturing to the overall GDP, though that was, I mean, way too low compared to what we have today, was nearly 40%. A country like South Korea has actually that level of contribution to their GDP, 40% plus. There are many other countries, small countries though, where the manufacturing actually contributes a very major portion to their overall country's economy. Now, in India, we have enormous opportunity. More than anything else, we have possibly one of the largest economy and one of the largest consumer market in the entire world. So obviously, there is enormous scope for manufacturing. But today, according to Director NIMT, we must focus on remanufacturing. So on a Sunday morning, he made me study what is remanufacturing. And according to Dr. Google, it is rebuilding of a product. Let me open my pointer. So it is rebuilding of a product to specifications of the original product by combining reuse, repaired, and new parts. Now, when we talk of new parts, actually, it is not just repair or refurbishment only for life extension, but it's actually an activity leading to a new lease of life. So essentially, we are talking about a new cycle, new use cycle. There are many components I found in the net, which actually are already very routinely produced and remanufactured. And it is not just one or two components, but essentially the entire system is remanufactured. And here the new product essentially is not just in terms of appearance, but primarily in terms of performance and service life. But I'm not an expert. I'm an expert of practically nothing, but I have some knowledge about surface cladding and additive manufacturing using laser as a tool. And I would like to use that as a possible means of approaching the concept of remanufacturing. So I gave the title of my talk as Laser Surface Cladding and Laser Additive Manufacturing as precursor to remanufacturing. And this is how I established the connectivity with this subject domain. So imagine a complete turbine engine. You have the compressor, you have the combustor and the final turbine blades and so on. It costs, enormously large. I mean, for an aircraft of the total dead weight and the total number of components, this is not only the most crucial, not only aircraft, even for energy manufacturing units and so on. This is one of the most expensive and obviously the most crucial part. So if you can remanufacture this, then obviously you are talking about a very large amount of cost saving. So if this is the nozzle, which is in original design, which has 13 parts, and if you can prepare the same thing by an additive manufacturing approach, you essentially are talking about a single part. So all you have to do is to serially section in the vertical direction, layer by layer, and then allow the beam, which actually governs the deposition of the metal, to trace exactly that geometry so that vertically, section-wise, you integrate and create one single part, which is the total nozzle, including the head, the fuel mixture, and the swirler. So that's the power of additive manufacturing. But I'm not straight away going into that. I would like to draw your attention to components. Say, for example, this pressure bucket is a very expensive material, very expensive component, and these teeth are the most crucial part. And since while digging the earth or the freshly mined products, there's every possibility the tip gets damaged very easily. Now, in ideal situation, this is not just a monolith. These are at least 5 or 6 different components which are joined together, riveted. But if this whole thing can be remanufactured, then the earth moving industry and mineral processing industry or mining industry will enormously benefit. Similarly, look at these rolls or the wheels, where the rolling contact fatigue is the key reason for damage and life reduction, be it for wheel flat or spalling kind of a damage occurring onto the flat but curved surface, curved surface, but with a smooth contour. So these chip off portion happens because of cold welding, and in some cases because of the fatigue damage, rolling contact fatigue damage happening over a period of time. Similar things is true for, say, hydraulic cylinders, which is a very common component in the marine propellers or the mining components. Even hollow railway wheels, these damage in the top part clearly shows that this damage occurs over a period of time and progresses. And that exactly is the reason why these needs early replacement. Look at the continuous caster. From the turn dish to the nozzles through which actually the hot metal goes vertically into the rolls. And now you have series of rolls, and these series of rolls not only are responsible for thickness reduction, but also heat extraction and turning a skin depth solid layer into a completely solid sheet by the time it comes out of this train. Now, these rolls actually encounter very major damage because of high temperature, high corrosive environment because of the fluxes used, and also the mechanical forces. So together they create a very, very challenging situation. In fact, if you can see that these are some of the damaged parts. Now, when you actually are trying to remanufacture, there's no need that you have to remanufacture the whole trail altogether. They won't need that either. But certain pair of rolls certainly will require replacement. And so the roll here actually is a fit candidate for such remanufacturing exercise. So now let me refer to some activity we did nearly 8 years ago. Gururaj Telsang was our PhD student at Kharagpur. He's now a senior scientist in ARCI Hyderabad. Gururaj showed something very interesting. He showed that if you have H13 tool steel, in fact, this was basically a die component for pressure die casting. So this die, when we made laser cladding with the same H13 tool steel, so H13 tool steel pressure die casting die overlaid with laser cladding. And what we showed that if you actually, the clad layer was actually 3 millimeter thick. So if we could easily machine out very carefully though some 2 millimeter thick micro tensile components. And if you just look at, without going into all those details, if you just look at, compare the curve 1 and curve 4. So curve 1 is the H13 in the pristine condition, and 4 is the condition, 4 is the result from the clad zone after not only cladding, but also subsequent tempering. And this shows higher strength, yield, tensile, and even higher ductile region, higher deformation region, plastic region. So higher toughness, higher strength, higher longevity of the material of a refurbished component. So that means here is also another very enormous scope of remanufacturing of pressure die casting dies and tools, which actually can be remanufactured and can lend a better life than the original one. And what is interesting here, at least from the metallurgical point of view, is that I personally was quite surprised to see that this is a cast product, right? I mean, cladding essentially is a solidification product. So here we don't have a lot of retained austenite. Instead, we actually have more volume fraction of martensite than the original component. And why is it so? So you are solidifying steel from molten state all the way to room temperature. And during that, because of high hardenability, the steel not only solidifies into austenite, but also undergoes austenite to martensitic transformation during the same continuous cooling process. So, and since now the lathe size is finer than what could happen in a bulk, because it's happening only within 1 or 2 millimeters with a very fast self-quenching, so the platelet size is much smaller. And as a result, we get not only higher strength, but also higher plastic region. So just 1 or 2 things that why we are interested in additive manufacturing is purely because if you do subtractive, you create so much of a waste. If you do additive, practically no waste. And there is enormous amount of advantages in terms of design, flexibility, precision, accuracy, practically very little of tooling required, no further machining. And this is a very fairly green and clean manufacturing process, and is amenable to almost all kinds of materials. Ceramic is a suspect, not yet very popular, but metal polymer for sure. And you actually is ideal for high cost, low volume products. So essentially, this is something to be understood that if you are producing a small stamping product, then a stamping operation is much faster than any other competitive processes. But if you're doing a hard weld, for which you are ready to pay any amount of money because of its novelty and precision, then additive manufacturing certainly scores over the rest. So there are also limitations about size, about productivity, and so on. But the most important thing is that an industry which 20 years ago was $1 billion, in 2018 itself was one order of magnitude higher, and now the projection is by 2025 the amount is going to be some 23 or 25 billion dollar market. So there's a huge market and expanding every day. The novelty arises from the fact that cost per component is practically independent of the complexity or customization. Whereas for a regular product, every time you change, you have to change the die, you have to change the tool, you have to change even the entire supply chain management. But here the material, if the material is the same, then all you have to do is to go to your design table, change the computer-aided design prescription, and as a result, you can change the dimension in no time. So cost is independent of the complexity or customization. More importantly, that conventional manufacturing actually is more economical only when you are going to a much larger number of components per unit time. So the cost is more competitive for additive manufacturing when we are doing only a few. So that's why I said low volume, high cost components are ideal for additive manufacturing. Now, the confidence that with which I'm speaking today that additive manufacturing, cladding, and eventually remanufacturing all are possible using laser as a tool emanates from the fact that in 2019, we established this laser processing laboratory at IIT Kharagpur, 6 kilowatt fiber delivered diode laser with a 6-axis KUKA robo arm and with a powder delivery system. So in this, we have been able to produce many results which actually covers joining, alloying, cladding, refurbishing, various other operations. And I'm pretty sure that actually a finished component is quite possible, though we don't have that level of competence as yet. But this is a complete laboratory which actually can do all kinds of material processing, except, of course, oxide ceramics, and produce either clads or three-dimensional products and a complete system as well. We all know that laser is very interesting and very much attractive to us because of these reasons: coherence, monochromaticity, very low divergence, and most importantly, very high power density at exactly the spot where I want. So in other words, we actually can produce the exact heating and cooling profile, thermal gradient, certification velocity, depending on where I want. So where I place my focus. And this is an extremely fast process because there's either for direct band gap or indirect band gap materials or no band gap materials like metals, the excitation of the electrons to the higher energy state and falling back to the ground state, and in the process absorbing the incident photon energy and converting that into lattice heat is possible only within less than nanosecond, between nanosecond and picosecond. So extremely fast heating and cooling process. And we know basically also the other advantage is that the heating profile is exponentially decaying. So the heating zone is confined only to the near surface region, which could be just a few micrometers. And only two process parameters, the power density and interaction time, can actually allow me to go to heating, solid state, melting, vaporization, and in the process do all kinds of materials processing that one can think of. Two approaches. One is powder bed fusion. We don't have that, and I'm not much experience or exposed to that. But this is primarily for manufacturing industries because you don't have you actually require a large volume of powder because you use a powder bed. Whereas for research, we prefer direct energy deposition, which essentially means that you're able to not only throw the laser, but at the focus, you're also actually able to feed the powders, which melt and deposit onto the substrate, and then develop the three-dimensional product. Now, onto the specific examples. So Manoj Kumar basically wanted to develop thermal barrier coatings and oxidation resistant materials. And here's the first example, which is decades old, Jyotsna's work during her PhD. And it was for the first time we showed that instead of oxide barrier coating, if we could have silicides, intermetallic phase, which are much more compatible to the metallics base than the oxides, if they make up 85% of the volume fraction, either as the primary phase or as a part of the eutectic, then instead of this kind of an easy oxidation process in the base metal, which is titanium in this case, you actually, when you create such a barrier layer, then you prevent the counterionic transport of the oxide coming from outside and cation going inside, outside. So this oxidation is prevented. And as a result, if this is how titanium oxidizes, this silicide layers reduce the oxidation rate so significantly, even at fairly high temperature. So this is what we showed long time back. And then subsequently, we repeated this with nimonic alloys and also dispersed borides and silicides in stainless steel and developed such composite structures. And borrowing from that, Manoj actually wanted to create these thermal barrier coatings. So initial approach was with thermal spray followed by laser melting. And we were able to produce this very nice structurally and functionally graded component, with the top layer being oxide primarily with certain controlled porosity to reduce the thermal conductivity. But then you need a bond coat, you need a substrate. So obviously this cohesion here is very important, and the top coat has to connect well with the substrate because of the bond coat. So you have possibilities of creating 3-4 different layers, and each time you have to change the from vapor deposition to thermal spray and so on. So it's fairly cumbersome process, and interface is fairly sharp. So that's another major disadvantage, because of which spoliation can happen. So we actually tried also developing borides and nitride level of coatings. We also tried bulk metallic glass coating. In fact, to our surprise, we thought that would be an ideal universal solution, that if you can have such a bulk metallic glass, so there'll be no grain boundaries, so no boundary diffusion, and hence the oxidation or corrosion could be significantly reduced. But what we realized that even despite 10⁵ Kelvin per second cooling rate, still in that small amount of melting time, if you have components like boron, carbon, or yttrium on one side and nickel or iron on the other side, even in that small melt pool time, residence time, the two elements which are very different in density, melting point, specific heat, they have enormous attraction for each other, and they combine and form such multiple carbides, borides, and so on. So it is no longer a single phase. The clad is very good, gives you wear resistance, but it's not a single phase product anymore. So this is just the metallurgical aspect of it. But what is interesting is that Manoj actually proved that if you, instead of going for oxides, if you go for silicon, aluminum, or borides, then you end up making an interface which is perfectly compatible. And as you can see that some of these columnar grains are growing nicely and epitaxially from the base substrate into the very fine structure. So this is how it looks at the interface, and this is the alloy zone. Whereas from the top surface, this is the kind of microstructure you develop. So this basically is very useful. This is the hardness profile, and this is all the diffraction evidences about the phase aggregate and their identity and distribution. And this is the microcompositional profile to show that there is indeed compositional gradation. And this is the evidence of the oxidation resistance. And you can easily make out that if this is how Inconel 718 undergoes oxidation at the reference temperature, then after alloying with silicon and having so much of silicide in the microstructure, this is so significantly you can reduce the mass gain, or you can improve the oxidation resistance. So I'll skip the remaining. This is what is interesting also is the fact that if you look at the post-oxidation XRD analysis, then you realize that this phase aggregate not only has oxides, but also some of the pristine intermetallic phases. So in other words, despite exposing to 100 hours at a fairly elevated temperature, still you are left with unconsumed or unconverted intermetallic phases. So that means these intermetallic phases, because of their high stability and high melting temperature, are still not oxidized, and they can continue to give you a good amount of oxidation resistance. So here is an example that what happens if I mix stainless steel with 718 and do a gradation. 100% stainless steel base substrate, 75-25, 50-50, 25-75, 100% Inconel. So I have a stainless steel component and I do compositional gradation, and then finally I have only Inconel 718. So I don't need a separate stainless steel, I don't need a separate Inconel component. I can, because the temperature, whatever I'm using, stainless steel can very well withstand, but stainless steel cannot withstand the oxidation at that temperature. So I make the surface with 718, and these are the diffraction analysis profiles, which shows that what are the phase aggregates. This is how the composition varies, and this is how the hardness and other properties change. One other important aspect, while you deal with this, then you graduate. This is Manish Naik's work. If you just compare these pairs of microstructure here, the one on the left and the right, same material, same cladding routine, same parameters, absolutely everything same, except the state of the substrate prior to cladding. So this was sandblasted and this was built subject to belt grinding. So sandblasting causes more roughness and hence more scatter and more laser absorption. So interdiffusion or intermixing of the clad and the metal is fairly large. So this melt penetration zone is thicker in case of sandblasted samples, whereas after belt grinding, you don't have so much of roughness and hence laser coupling is low. And as a result, you retain higher hardness, and the phase aggregate also is pretty much, by the way, I forgot to tell you that here the cladding is triple I 400, which is a multi carbide boride mixture in martensitic base. And so they actually can provide you very high, not only wear resistance, even corrosion resistance, provided you maintain the thickness well. This is from Nikita Mohite. She is an employee of Hoganus Pune, and she is interested to take care of these casting rods and their damages. So her job is to try, this is 4140, the base steel, martensitic steel, low alloy martensitic steel, and she wants to try out with SP616. These are all trade products of Hoganus. This is very similar to 4140, but Rocket 431 is again a martensitic variety. X402 is possibly super austenitic variety. So she wants to try cladding and then refurbishing to an extent that the roll can be reused for a new lease of life. So this is the kind of cross-sectional microstructure. This is the clad zone. This is the interlayer or melt penetration zone, and this is the base substrate. The similar approach Mangesh wants to do with these railway wheels. So he basically is dealing with two substrates, 4140 martensitic steel and 1070, plain carbon steel, but near eutectoid. So in such cases, he again is interested to actually clad Rocket 401, which is a multi-carbide martensitic clad material. So this is the clad zone, and this is the melt penetration zone, and this is the base substrate. So what is interesting is that though there is substantial intermixing in the melt penetration zone, but the composition is primarily the clad composition at the top layer, and only here you see levels of intermixing. But this is desirable because then you don't have a sharp interface, and there is a very good bonding from substrate to melt penetration and melt penetration to the clad zone. Now, this is only the cross-section of a thin layer. One can certainly build a much thicker layer, and then eventually I'll show you some other examples. So this is what Shubhra Kamal is doing, and this is a very interesting piece of work because he's trying to do what Manish was doing with on mild steel. He's doing the same thing using triple I 800, not triple I 400, on stainless steel or Inconel or some other expensive materials. So this is how basically, so this is the wear volume. You can easily see that as we take stainless steel and compare with various forms of triple I's, with triple I 800, the wear volume is the least. So obviously this is the most wear resistant material possible. So these are the varieties that we are seeing. And here is an interdiffusion zone, but this is the clad layer. And this is the top microstructure. So as you can see, this is primarily with plenty of intermetallic phases, including Laves phases. In fact, triple alloy series actually has a good volume fraction of Laves phases. And this is how the micro hardness profile varies. And as you can see, with 800, you have the highest possible hardness, whereas in some other cases, you have lower hardnesses. And this is the clad surface, and this is how the wear track varies as a function of depth. So we can build such layers, and these could be functionally graded. So I can mix 10, 20, 50, 100% and change accordingly so that the compatibility is better. But in case of pure triple alloy 800, we have a vertical crack here because they have multi-phases, including Laves phases. So obviously they are prone to cracking. When I do it with a functional and compositional grading, then there's no such cracking and it's perfectly compatible throughout. So this is a good news. And this is a kind of 4 centimeter, 6 centimeter layer that was built. And as you can see from different regions, how the microstructure varies. So this variation of microstructure from the base substrate and solid liquid interface all the way to the top surface, which is pure T800, you see a gradual variation of microstructure makes it fairly compatible. And as a result of which the material will have a much larger life and compatibility. So this is interesting piece of metallurgy. I hope, I wish I had more time to discuss with it. So essentially, we know basically in case of solidification processing, there are 2 important aspects we are talking about, the thermal gradient and the growth rate. And with this, I can actually create a process map. And from that, I can predict under what regime I'll have very high G by R ratio and hence a planar growth front. And on the other hand, what would be the lowest range of G by R ratio so that I can get equiax structures. So in the process, this is how I can control the microstructural gradation with increasing or decreasing amount of constitutional supercooling or the phase separation or solute segregation during the processing itself. So I'll skip this part. This is the wear, volume, and tribological aspects of this entire cladding process. This is also very interesting because, as you can see here, the red bars here refer to the wear, and the blue bar refers to the hardness. So it's not always true that high hardness means higher wear resistance, but here we see a nice correlation that with stainless steel substrate, we have the highest wear volume because we have the poorest hardness. On the other hand, when I have pure T800, then I have the highest, nearly highest hardness and the least wear volume. So we have to play with it, and this is what you're seeing as a function of various laser parameters. So with this, I'll try and wind up now. So, I thought of it. I hope the manufacturing community will agree to my conclusions. See, when we talk of cladding, you see, cladding is basically a layer-wise deposition. You have one layer, second layer, third layer. Additive manufacturing is a droplet integration process. So you go droplet by droplet along X, along Y, then along Z. So this is how you build a 3-dimensional structure. So you actually can build 1, 2, or 3-dimensional structure and make a full component or a full device. So remanufacturing, in my opinion, can largely benefit from the established technology and knowledge base available with the cladding and the additive manufacturing community and ensure a huge growth potential of this new technology. So remanufacturing, in my opinion, is a logical progression in that direction, what cladding and additive manufacturing already are able to do. But we need new job shops, areas where one can try this out. And we actually also require materials with desired composition, shape, size, morphology to feed in, and then create the fusion zone and then build the 3-dimensional structure. There are a lot of metallurgical challenges in terms of the powder grades, the interface, the oxidation, segregation, controlling the various thermodynamic parameters, roughness, and so on. Also, we need competent manpower who actually understands the process well. So obviously, it will emerge in course of time. So in my opinion, there are plenty of opportunities which we are yet to explore or maybe even appreciate. So thank you very much. I hope I could make some sense to the community.
Professor Manna, I will take only 30 seconds. We are really thankful to you because instead of your engagements, you could make it happen. What we understood it is true that he started looking at remanufacturing this morning only, but what he made us understood that it is an important variant of manufacturing process in between conventional manufacturing and 3D printing, where we can use a simple code and we can improve the performance even better than original component by customized development of layer by layer with tailored microstructure and phases. So we are really thankful to you. So this definitely sheds some new light in the progress of remanufacturing in future. Thank you.
Thank you, Partho, and thanks also for making me learn the new subject, though on a Sunday morning. And also my apology to Soumitra for gate crashing and replacing him. So with your permission, Partho, I would like to now exit.
Sure, sure. I understand. It is now 11 plus.
Right. Okay. Thank you very much.
Thank you, sir. So now we move for our next session. So we very welcome to our honorable speaker, Dr. Soumitra Tarafdar sir, and all the panelists and all the participants of these sessions. So before over to the sessions to the honorable speaker, Dr. Soumitra Tarafdar sir, it's my indeed privilege to introduce our noted eminent researcher.
Dr. Jageshwar Verma, I will take 1 second because I must say, definitely, I mean, Soumitra is a good friend of mine. We studied together from BTech. So I'm not going to say thank you to him, but I must mention that I started, I mean, with this subject, to conceive the subject, to make a framework, to take a decision to pursue this particular subject at personal level and at institute level. With Dr. Tarafdar, we had a good amount of discussion with him, and that's how we could configure this workshop. Thank you.
Thank you.
Thank you, sir.
Can I share my screen?
Before that, yeah, you do that. Before that, Dr. Jageshwar Verma wants to introduce your
Profile, sir.
profile.
Okay.
Sir is a former chief scientist, CSIR National Metallurgical Laboratory, NML, Jamshedpur, India. Sir is a professor, academic of scientist and innovative researcher, CSIR National Metallurgical Laboratory, NML, Jamshedpur, India. Sir is going to deliver a lecture on application of non-destructive evolution for integrity assessment and residual life prediction in regenerative manufacturing. Sir did his Bachelor of Engineering from Bengal Engineering College, Sibpur, MTech in IIT Kharagpur, and PhD from Cambridge University, UK. Sir is an expertise in the area of fracture mechanics, mechanical behavior of materials, failure analysis, and structure integrity evaluation. Sir has several awards and recognition in his credits. He is a fellow of Indian National Academy of Engineering in 2013, Metallurgist of the Year Award, NMD, Ministry of Steel, Government of India in 2010, Professor V.A. Altekar Award of Best Technology Transfer from NML in 2007, Best Paper Award R&D category, National Seminar on Non-Destructive Evolution, Hyderabad in 2006, Award for Excellence in House Research, National Metallurgical Laboratory 2004-2005, 6 and 2030. Dr. B.R. Nijawan Award for Best Technical Paper, National Metallurgical Laboratory 2003, 9 and 2015. Indian Institute of Metals Award for Presentation and Metallograph at Annual Technical Meet in 1997, 2001, 2005, 2006, and many more. So we proud to have Dr. Soumitra Tarafdar sir for these sessions. Now I over to the sessions to the Dr. Soumitra Tarafdar sir, please.
Thank you. Thank you very much. I'm not all that you read about. Well, some of them just come and go. But I must say that I'm very thankful to be here today in this workshop as a speaker. And I thank the organizers, NIAMT, and FAMFI for giving me an opportunity over here. A very good morning to all the people who have joined in. And what I would like to talk about today is on structural integrity assessment. Well, as was mentioned, I am from the National Metallurgical Laboratory. I have superannuated now. And National Metallurgical Lab, or NML, is a constituent lab of the CSIR, the Council of Scientific and Industrial Research in India. And we, our group has been looking at structural integrity assessment at NML for the last 30 years or so. And what I present here today is on essentially structural integrity assessment and making some reconnections with remanufacturing. As a matter of fact, I'm really a novice when it comes to remanufacturing. In fact, this workshop and the discussions that Professor Chattopadhyay was talking about that we had when he was planning this workshop, and when I read a few papers and documents, is what gave me an understanding of what remanufacturing is all about. If it has to be understood very simply, I think this one slide gives it all. Essentially, it's taking used products and remanufacturing products with under near new conditions. So that is what remanufacturing is all about. You, of course, can take in a bit of new components or remanufactured components, and you do create a bit of waste, which has to be disposed responsibly. So this is the domain of remanufacturing. And when I looked at it, the type of activities or processes that are necessary for remanufacturing, particularly inspection, reprocessing, testing, are activities which are very similar to what we carry out in structural integrity assessment, and essentially for the same purpose. So this is the connection I wanted to draw today between structural integrity assessment and remanufacturing, and trying to tell that there is a host of skill, expertise, knowledge that is and technology that is available for structural integrity assessment, which can also be used for remanufacturing as we get into the domain of remanufacture and help to lay down a industrial backbone in India. So what is structural integrity assessment? When I talk about structural integrity assessment, essentially I want to state if critical structural components, for example, pipelines, boilers, turbines, or any other such engineering components, the failure of which is totally unpardonable, or the failure of which has to be avoided. When we try to understand its integrity status, structural integrity status, we essentially have to rely on three types of inputs. Three types of informations are required for it. Firstly, information on the material from which such components or structures are made. The material, of course, this can be documented already from the OEM, but sometimes the material degrades when in service. And you have to understand the type of degradation that has taken place in the material also. You must also have capability to do non-destructive surveillance. That is a very important aspect of structural integrity assessment, because through this, you understand the damage and the location of damage that is happening in the structural component. So non-destructive surveillance. And of course, you must have the ability to simulate and model that structure and component for such as a simpler thing as stress analysis, or even the flow behavior of fluids that might be there in the component and structure, the temperature distribution, so on and so forth. And also be able to model the inputs that you get through non-destructive surveillance and from the material characterization in order to carry out structural integrity assessment. In fact, from the material, based on the material, you have to obtain the damage resistance data of the material. Now, this can be as simple as how the strength of a material deteriorates with service, let's say at high temperature. It can be as simple as that. or it could be how fatigue crack growth rate or the fracture toughness or the corrosion rate or whatever of the material. Much of that information is already documented in the literature, but sometimes you must have the ability to experimentally evaluate and obtain such data. Once you have all these data, then you combine the information that you have, use standard procedures, protocols that are laid, using sometimes codes and software that are available to carry out structural integrity assessment. So these are the various types of activities that are necessary to carry out structural integrity assessment. And at NML, we were trying to do some R&D on some of these aspects in order to develop further some of the processes, the protocols that we have for structural integrity assessment. Having said that, the proof of the pudding is often in its eating. And at times in structural integrity assessment, you have to sacrifice a component or structure, do a full-scale testing, and ensure that the integrity assessment that you have proclaimed meets your predictions. So this is what structural integrity is all about. It didn't start off as structural integrity assessment. Let me just give you a bit of history. In the late 60s, it started as a proposal for assessment of fitness for purpose. And it was primarily for welded structures, because welded structures were deemed to contain defects inherently. And it used fracture mechanics principle in order to carry out this fitness for purpose analysis. But over the times, it was found that the same principles can not only be used for welded structures, but for any critical structures. Because during the manufacturing stages, there can be defects which are incorporated into any structure, or during the operation or service life of a structure, there can be defects that are generated. So you can use the same principles, and it began to be known as engineering critical assessment. But then, over the course of time, over the further developments, when damage was not only thought to be cracks or defects, like crack-like defects, but any type of damage, maybe creep damage or corrosion damage or tribological damage, the scope of the assessment broadened, and it was called structural integrity assessment. So that is what has been happening through the last maybe 40, 50 years. Very recently, there has been a slight tweak to the approach. In fact, depending more on non-destructive surveillance and on modeling, using various types of analytical as well as heuristical model. And the spin-off is called structural health monitoring. We'll dwell on this briefly as we go along. So, and there has been a lot of other names in due course, which have been offshoots or which have been specific domains of structural integrity assessment activities, or remaining life assessment, condition monitoring, assessment and refurbishment, repair and rehabilitation, reliability and risk management, so on and so forth. So these are special domains which are offshoots or within the structural integrity framework, which have been important, and I'm sure some of you may have heard of this at some point or the other. So what we are talking about, as it started with fusion welded structures initially, is the undesired confluence of a defect, a crack-like defect, the stress situation in the component, and the resistance to further failure given by, let's say, the fracture toughness of the material. So at the undesired confluence of all these three, we are going to have failure. So fitness for purpose or engineering critical assessment was more about finding out the boundary of this undesired region and making sure that you're beyond this, so that you can proclaim that your structure is safe, that your structural integrity is maintained. Over the years, what has happened is you can now look at any critical structure and not only talk about crack-like defects, but any type of damage. It can be a corrosion damage, a creep damage, as I said, I'll come to those later on. As long as you have the damage resistance data for the material or the degrading or the evolving material that you have in service, as long as you have that, And as long as you have a good handle or understanding of the operating conditions, you can find out the undesirable confluence of all these and make sure that your component is beyond that undesirable area to proclaim that your component is structurally sound. So this is what structural integrity assessment and its offshoots are all about. When it comes to remanufacturing, this is my thought, that you are just trying to do the same thing, maybe in an opposite way. You are trying to see that the damage that can be there already in a used component is not too great to cause a failure. And in order to assess that, you must have some information on the damage resistance of the material of which that component is made. And you must have knowledge of the operating conditions. So maybe you redraw the boundaries, you redefine what you think is failure and what you think is reusable, and everything outside is what you can reuse. You can use for remanufacturing. So there is a lot of commonality. I think the philosophy is all the same. It depends upon how we are doing it, what are the regulations, the laws, the normative conditions that you have, and what you consider as your threshold for reusing a component. So the knowledge, the expertise, the technologies that are available for all this can very much be tweaked in order to use them for remanufacturing. So these are my thoughts, and that is what I'll try to propagate or promote during this talk. There has been a lot of developments, of course. This is only trivia of the various schemes and the programs that have been there throughout the years in Europe, in USA. Of particular note is this American Petroleum Institute's API 579, which was so important for structural integrity, which was promulgated in 2007, and so on and so forth. One thing to note is in recent times, there has been a lot of development of software platforms for carrying out structural integrity assessment or part of structural integrity assessment. And that has made life much simpler, in fact. There is a host of guidelines and softwares. Particular mention is in the British standard 7910. They actually came out with a standard, I think in 99 or 2000, called Method of Assessing the Acceptability of Flaws in Metallic Structure, based on the engineering critical assessment principle. And also some of the sections and the appendices of the ASME boiler and pressure vessel code, which talks about the procedure for structural integrity, and the court cases, which tells you how to proceed in order to calculate if a structure is safe or not. There are, of course, military standards in effect in US Air Force for designing aircrafts based on fraction mechanics criteria. The bridge evaluation manual of the American highway, etc. So all these gives you, for different classes of components, different types of damaging conditions, the way you go ahead for doing structural integrity assessment. So I was talking about structural health monitoring. So in this gamut of activities, all of which belong, I think, to structural integrity assessment and its practice, structural health monitoring consists of a shortcut. And it is this. You rely heavily on sensors for non-destructive surveillance of your critical structures continuously, very often, and rely on modeling. And these models are based on huge amount of data of these type which are already built, the knowledge that is already there. Or sometimes the model can be just heuristic based on a huge amount of case studies. And you predict, based on certain norms, the structural health of a component. So this, in short, is what structural health monitoring. It also determines the damage, its location, it quantifies the damage, and then predicts, based on models, the remaining life of a structure. Just to give you a simple example, if you have a structure like, let's say, a bridge, and you can excite it, know the excitation, you get a dynamic response. Knowing the type of structure, you can use analytical or numerical models, and knowing the excitations, you can work out the type of dynamic response. Structural health monitoring is like an inverse problem. So here you know the excitation, you know the response, can you tell what type of damage has taken place in the structure? And for that, there are various types of models based on which the health monitoring is done. So there can be models, as I said, based on a lot of data that is already available on it. It can be based, it can be analytical models, or it can also be heuristic models that are possible. And in recent times, the structural health monitoring has shown enormous progress. For example, for the aerospace industry, a steering committee was set up in 2006. And by 2013, within 7 years, first guidelines for structural health monitoring of commercial aircrafts were issued. And they were obviously useful because by 2016, the US Air Force, for its structural integrity program, the ASIP, as it is called, which is very popular, it included the structural health monitoring protocols proposed in these guidelines as an in situ non-destructive inspection method in its manual. So all these developments, I think, are things that remanufacturing concepts or remanufacturing paradigms can actually borrow because they are pretty well developed. All that is necessary is perhaps redrawing our thresholds, what we consider to be safe, what we consider to be reusable, what we consider is minimum damage so that we can still accept it for service. So that is my contention. Again, for structural integrity assessment, you require a multidisciplinary approach. You require a good knowledge of the materials. You must have a good handle on modeling. You must know the stresses, have good non-destructive evaluation capabilities, maybe specific domain knowledge for, let's say, corrosion or fracture, depending upon what's happening to your structure or component, and multidisciplinary approach to the problem. The same is true for structural, for remanufacturing also in many ways. So I've been talking about damage. What is damage and how is it caused? Where is it located? And how do we quantify it? We would like to quantify it non-destructively. But for that, we must understand, if necessary, destructively, how the damage happens. So let's take the case of metallic components, which I'm more familiar, or many of us are very familiar with. You can define a metallic material by its microstructure, by its chemistry, crystal structure, the defects that it contains, the grains, grain boundaries, or the orientations of the grain that you have in the structure, the phases that are present, or some of the inclusions, precipitates that are there in the structure. So all these help us to define a metallic microstructure. Whenever there is an external stimuli on that microstructure leading to damage, let's say whenever there is a stress that is applied on the microstructure, there is a resultant response as a deformation, and it's often can be measured or quantified through the accumulation of strains. The stress can be very small. It can be, let's say, for a fatigue type of situation, repetitive in nature. There can be environments which influence how the primary damage is established through deformation and accumulation of strain. Let's say temperature, let's say a corrosive environment, all that will influence how this takes place. But that per se may not be damage. This is only the start of damage, and we can live with that. What happens is when there is a sustained application of stress, maybe cyclic in nature, monotonic in nature, the environment, the other materials that are there in the neighborhood, etc. This initiation of damage further interacts with the microstructure. The strain interacts with the grains, the grain boundaries, with the inclusions, with the precipitates, and this, in a sustained and cyclically, it increases the damage. So as the external stimuli is sustained, this will further interact and cyclically be processed within the microstructure and the resultant to cause damage. That damage will be reflected in increase in, let's say, the dislocation density, so some of the defects in the microstructure, or changes in some of the inclusions that you have, the phases that you can have, the phases can transform. There can be changes in the grain orientations, the grain boundaries, they can slide, they can move, they can grow, so on and so forth. And that constitutes damage. When the damage reaches a critical amount of quantum which can be tolerated, then fracture takes place or failure takes place through the creation of surface. So this is the total process of a material going through, let's say, deformation, accumulating damage within it, and then when a critical amount of damage has been accumulated, there is fracture. So we get our mechanical properties from this deformation aspect. We get our fracture properties from this creation of surface aspect. But realize that everything is from the same process. It's part of a whole. And therefore, all these are related. So you can actually relate the microstructure to the mechanical properties. You can relate the microstructure to the fracture properties. And you can relate the mechanical properties with the fracture. This is all part of a whole. So this is what we mean by damage and how it is incorporated, talking very philosophically, in a particular structure. Let's look at some of the typical damages that take place. This is not an exhaustive list. This is just what I've made. So in engineering materials, how can these damages occur? Which are the external stimuli that can give rise to some damages? So the damage can be due to unwarranted load excursions, like impacts or overloads. It can be because of fatigue, when there is cyclic or fluctuating loads, and fatigue damage occurs. It can be at elevated temperatures, creep damage. Of course, at elevated temperature, there can also be microstructural degeneration. And this microstructural degeneration can also be because of corrosion, when there are certain environmental conditions. Corrosion itself is very important on the surface, and the surface properties gets lost. Oxidation, tribological damage because of wear, abrasion, all these are damaging mechanisms which are particularly prevalent on surfaces, and they have to be quantified, and only then you can tell if a component can be used for remanufacturing or refurbished, repaired, and used for remanufacturing. In the last lecture, we heard that how some of the surface processing by laser can be used for repairing and refurbishing these components. And there can also be synergistic damage due to operation of more than one damaging mechanism at the same time. So these are the processes by which damage is created. And in structural integrity, as in remanufacturing, we have to be able to quantify and locate this damage and make sure that the damage is acceptable for the structure to be called to have integrity, to be safe, to have remaining life, or for a component to be reused in remanufacturing. So that's the basic concept, and I think the concept is essentially the same. So in order to locate and quantify the damage, at NML, we had been working on the development of a number of tools and techniques with which we can do it. And these are all non-destructive inspection tools. And these are all tools which were not really available in the market. There's a lot of tools that are already available in the market. In fact, I may not be the best person to tell you about that. There are experts in the market who can tell you. But what we were trying to develop is tools which are one generation ahead. These two, the Maxis and the MagStar, were non-destructive tools based on the magnetic hysteresis loop and the magnetic Barkhausen noise, through which the degeneration of a microstructure when it is in service can be quantified. Because that becomes a very important input whenever you are trying to decide if the component is safe or if the component is reused. So these two, the Maxis and the MagStar, are based on magnetic principles. particularly magnetic hysteresis loop and magnetic Barkhausen noise. And these two devices that were developed by us, the technology was transferred to manufacturing units, and these have been commercialized and are in service. The Ultra Beta is a device which is still under development, I would say, but it was very, very promising. It depended on ultrasonics, particularly non-linear ultrasonic, in order to quantify the damage that is created in a component structure. I'm going to talk about some of the background developments of, in the realm of our R&D that led to the development of this Ultra Beta, which is a portable device which can be used for non-linear ultrasonic examinations of certain type of damages. Non-linear ultrasonic is quite prevalent, but using it for certain type of damages, there is a bit of twist in it, and that is what we were looking at. FlowGuard is a device that is again in the market. It's used for looking at damages that have taken place during manufacture in wires. And it is in place in a number of manufacturing units in the country. And this is again a thermography-based device to sort out materials in the incoming phase. So these are some of the devices that we have been working on at NML for the last 20, 30 years. And some of them, as I said, have been commercialized. Some of them are in the process of development, and a lot more are still in the process of development. We develop our own sensors, do the background R&D to calibrate the devices, develop our devices, all the electronic and the software part of it, and then transfer the technology to a third party who are going to manufacture it, package it, and sell it in the market. Another device that we have developed is a minimally invasive device for mechanical property determination. It's called the automatic ball indentation technique, not something new that has been there in many parts of the world, but very costly. So we developed our own version, and we developed for our atomic energy units for looking at the degradation of mechanical properties of some of their components in service. For example, this heat exchange pipe. You can strap this device onto the component, and it makes a very small indentation of about 1 millimeter diameter and very shallow, which can actually be left behind there for certain types of components like this pipeline, because these are thick components. And you can determine how the mechanical properties have been degraded during service, if at all, and therefore thereby understand the structural integrity concept. So let me just present a few of the background R&D that we're doing. For example, to non-destructively evaluate fatigue damage. How do you do it? And this is all with non-linear ultrasonic. See, as I said, when there is fatigue damage, essentially what happens is the dislocation configuration in a material changes. So it goes into a cell type formation, some amount of dislocation, annihilation, subgrain formation, and then subgrain growth. And after that, a micro crack is initiated and the crack grows. So if you can quantify damage in these stages, you can say if the fatigue damage is sufficient for us to live with. And that is what we have been doing using nonlinear ultrasonic. The concept of nonlinear ultrasonic is actually very simple. If you use certain frequencies and impose that on a structure, sonic frequencies, let's say 440 and 8000 hertz, then that structure resonates, a bell resonates. And the resonated output from that structure can be again captured, received, and it will be the same as the input. So the output will be the same as the input. But if that structure contains defects, damages, for example, if there's a crack in the structure, then the output will have additional harmonics. So you won't only have 440 and 8000, but higher harmonics of 440 and 8000 of varying amplitudes. And this appearance of harmonics and their amplitude can actually be used to quantify the amount of damage. This is just an analogy, but this can be used for any material. So what we have done is we have taken a specimen, damaged it by fatigue, and then tried to monitor the nonlinear ultrasonic response of that specimen after it has been damaged, and looked at the total harmonic distortion that has happened in a square or the square root form. So again, this is what we have been doing, just zooming through that, using pure sinusoidal acoustic wave of 150 kilohertz initially. And this is the output that you get, the primary signal and the harmonics if there are. And what we find is this. See, when the material was without any fatigue damage, virgin, without any tests, we find that this is the primary signal that we were putting in, and there is a harmonic, because any material will have some dislocations, will have some damage already in it, a very small harmonic. But as we fatigue it, and when the damage is 60%, look at the increase in the second harmonic. When the damage is 95%, the increase in the second harmonic is much as that. So at least you can tell by a study of the second harmonic from nonlinear ultrasonic how much amount of damage that has taken place. So this is the type of correlation that we obtain between the total harmonic distortion and the percentage of fatigue damage. Percentage of fatigue damage given as a fraction of the fatigue life. And we find that replicate tests meet very elegantly. And we find that there is a region, if you are within this, perhaps you can say that you have less than 50% damage and perhaps it is safe. We also studied at various levels, the dislocations configuration was there to understand the type of dislocation configuration that takes place with fatigue damage and how it progresses to ultimately initiate a crack. So that was one of the studies. Similarly, for creep, we tried to understand if creep damage can be quantified using a non-destructive, nonlinear ultrasonic. So creep, as you know, is a very deleterious process for components and structures that are at high temperature, all your boilers, turbines, etc., where the creep rate initially decreases, of course, but the creep damage as a function of strain increases, and then ultimately it leads to failure. There are established procedures of doing a creep test, but the mechanism of creep is primarily through dislocations, by dislocation glide or dislocation creep or diffusion creep, depending upon the stress level that you have and the temperature. And of course, ending with grain boundary activity, sliding, cavity formation, etc., leading ultimately to failure. To give you very simply, dislocation creep is when dislocations glide and they climb across obstacles because of the elevated temperature. And that is what creep gives you and leads to the accumulation of strain, the accumulation of creep damage. When you have diffusion, so when you have, this is called Navarro-Herring creep or cobble creep, other than the dislocations, which of course participate, there's a lot of diffusion of the atoms that make up the grain. So diffusion through the grain body or diffusion through the grain boundary. That is what is the difference between Navarro-Herring creep and the cobble creep. And of course, when you reach the ending stages, you have a lot of creep cavities, you have a lot of grain boundary, sliding, and crack formation, which ultimately grows, the crack grows and leads to failure. So you have to avoid this obviously. But can you tell at what stage of dislocation or diffusion you are non-destructively in order to quantify the damage? So this is the mechanism map for creep. You have cobble creep, Navarro-Herring creep, dislocation creep, and dislocation glide. Usually components and structures are at a very small sigma by G, and your homologous temperature is usually above 0.4. So you usually have a combination of these. And unless this progresses to a high damage level, the failure does not take place. So can you quantify what you have? But quantification separately in each of these mechanisms is impossible because concomitant with creep, often you have microstructural degradation at a high temperature. So we again use non-destructive, non-linear ultrasonic, non-destructively. We tried to look at the microstructure. We looked at a standard 9 chrome 1 moly steel, which are used in boilers. And as it goes through creep, you can make out that there is a change in the structure, but very difficult to quantify. This was creep tested at 100 MPa at 650 degrees centigrade, which is typical for this type of material, maybe at a higher stress levels. But when you look at the type of dislocation substructure that is there through what is known as kernel average misorientation, because these dislocation substructures within a grain causes slight misorientations within the grain, parts of the grain to the next part of the grain, etc. And they can be revealed through electron backscatter diffraction studies to give you kernel averaged misorientation. And when you quantify this kernel average misorientation, you find that there is a progression. It may not be apparent to the eye, but I'll show you in a graph that there is a change. And concomitantly, simultaneously, we measured the nonlinear ultrasonic response of the material. So we are passing ultrasonic wave of a particular frequency, and we are looking at the harmonics that are generated and quantifying the harmonics by the beta factor. That is where the ultra beta name of the equipment came through, which is still under development. It has not been commercialized as such. What we find, the type of correlation we obtain, is that the beta factor has a very good correlation with the kernel average misorientation as a function of creep exposure. Similarly, the beta factor has a very good correlation with hardness, and the kernel average misorientation has a very good correlation with hardness, which essentially tells you you can use the non-destructive NLU parameter to quantify how the damage is taking place. So these are some of the background studies we are doing. I'll end. Do I have about 10 minutes? Can I take that?
Yes, sir.
Okay. So I'll end with some of the other type of structural integrity assessment activities that we were having, which is on repair of a damaged power plant. We were acting as in the capacity of a consultant really, and there was a vendor who were actually doing the repair. The owner of the equipment again is one of the power plant sector big companies. And we were looking at the work and we were trying to guide the work and make sure that the repair is done. So this was repair and refurbishment. Maybe the speaker coming after me, Professor Amitabh Dey, he would be able to speak about some of these welding repairs that I'm going to talk about here, but just to give you a glimpse of the type of work we have been doing. And just to tell you that this is not very far away from remanufacturing. You know, we call it repair and refurbishment, but essentially it was remanufacturing the rotor and putting it back to service. And I think because of the rules that you have, the laws that you have, the normative references that you have, we call it repair and refurbishment. But remanufacturing is perhaps just a step from here when you can actually do a bit of commercial activity with the type of activities that I will show over here. So this is the rotor we are talking about. It's a huge rotor, 76.9 tons, 8.7 meters long. It was part of a 500 megawatt system, which operated at 302 degrees centigrade. 6 stages, 6 into 2 on both sides, boiler side and the generator side. And one of the stages, the 4th stage on one side, during inspection, during a shutdown, was found to contain a defect. And therefore, and there was, of course, telltale signs of vibrations, of problems with its bearings, etc., which told the people who were operating it that they cannot operate this. And this was lying idle. This had worked for about 1 lakh plus hours with about 100 plus startup and shutdowns. But it was felt that a lot of life is still left in it. A rotor of this type can live for much longer. But because of this defect, what to do? And the problem is the defect was in the disc, which is part of the integral forging of the rotor. So this is the forging of the rotor. And these discs onto which the blades are fixed are integral to the rotor. And the defect was in this stage in the disc, the integral disc of the rotor forging. and how to repair them. It's of course very standard. You have to remove the blades, etc. And in the meantime, it had to be transported through about 1,500 kilometers to the place where it was to be repaired by again a very renowned people. And we were checking on how this was getting done and if it was done correctly. So this had to be turned, of course, for machining that part of the disc and then relaying metal over there through welding, submerged or welding, doing a post-weld heat treatment, making sure that the quality of the weld was appropriate, the material that was weld laid was up to the mark, it had the properties that were required, and there were no defects. So that was our part. So essentially part of the disc had to be machined off and relayed with weld metal, submerged arc welding. This was the welding wire. It had to be preheated, and think of such a big component which had to be preheated, and then post-weld heat treated afterwards. And during post-weld heat treatment, these are the parameters. It had to be post-weld heat treated to 580 degrees centigrade, but making sure that the temperature of nearby regions doesn't go much beyond 400 or even 300. So there had to be a lot of insulations, there had to be a lot of local heating, there had to be a lot of monitoring of the temperature profiles using thermocouples when the heat treatment, post-weld heat treatment was going on. And there had to be a lot of non-destructive evaluation, testing and evaluation to make sure no defects are generated. So if you look at the repair steps, there's a large number. Of particular importance is removal of the cracked area and doing a root cause analysis of the failure. Why did the cracking at all take place? So that you know that there was no inherent, large-scale inherent defect in the microstructure of the rotor, so that another failure does not take place in another place in the days to come after you have repaired and refurbished and put it back into operation. Then there had to be a weld mock-up before you can actually do the welding. And these mock-ups had to be microstructurally investigated, mechanical properties had to be determined in order to give the go-ahead that yes, you can go ahead with the particular steps of welding that was decided upon. And this was again upon us to decide and give the go-ahead. Then of course the welding, the preheating, the cool down after welding, which is very important to prevent distortions, machining and doing a very careful ultrasonic inspection. And I'll show you about some of the developments that have been there in recent times to do these careful inspections. And from the inspection, making sure that you can go in for a post-weld heat treatment. After post-weld heat treatment, again doing an inspection before doing a final machining. In fact, what we found is after the post-weld heat treatment, that there were 3 defects in the weld metal that was left. And through calculations, we found that at least 2 of the defects would be removed when the machining of the T-slots would be made in the weld-laid material. So that was not of concern, but one of the defects would lay there. And we had to do a fracture mechanics based calculation to see if that defect would grow with start and stop and how many start and stop it would survive, because we knew about the stress conditions in that location. So stress analysis was already done, so those data were available. And we found that that defect is not accepted. Now, having done all this, you could not again take out and re-weld and reheat treat the material, because that would make the material rest part of the rotor too much deteriorated to be covered. So it was decided that only a local, and you could not throw away the rotor, it was quite costly. So locally again, a repair and refurbishing was done. Not the whole disc, but only a small part of the disc where the repair was there. And we took special care to ensure that the microstructure that was produced was all right to survive the type of this thing that would be there during service. So after all that, the blades assembled were again assembled, sealed, high-speed balancing was done, overspeed checking was done, and this rotor was taken back by the owner for again reuse, and it has been used again. So this was repair and refurbishment. And I think it's not very different to what we are talking about in remanufacturing. These are some of the photographs that we have. The rotor, after the defective disc was parted from it, removed. Here is the defective disc which was parted, and RCA was done to find out the cause for failure. Machining prior to welding, when again, after which some amount of ultrasonic testing had to be done. This is after the welding, the final machining, when some defect was found and a local region had to be taken out and again rewelded, not to our liking, but nothing could be done. The post-weld heat treatment after the welding. This is the defect that was found in the existing fir tree in the disc, where the fir tree root for blade attachment is there. So we analyzed that crack and from where it came. These type of defects could be ultrasonically identified and located through these type of NDT techniques, ultrasonic techniques, to which I'll come later. The sectoral scanning technique using phased array techniques. So we looked at the crack, the microstructure of the welded material after post-weld heat treatment to make sure that it is accepted. So these were some of the work that was carried. If you look at non-destructive testing and evaluation, I don't like calling it non-destructive testing because there's a lot of evaluation in fact. There are various methods, and this is not an exhaustive list, but various methods of non-destructively probing a component or structures are available with us. And with that, we can do many things. We can detect a flaw and evaluate if it is acceptable. We can do leak detection, determination and defect and location, damage location. We can do dimensional measurement. But what we can, for all these, maybe some amount of standard equipment are available and quite popular. But the developments that are taking place will actually help you, and some of it is coming into the market, some of it that we are developing at NML or have already developed in NML, will help you characterize the microstructure of the degradation or deterioration of microstructure within cell. Give you the mechanical and physical property of the material, actually give you quantitative data, quantitative measurements. Tell you about the stress-strain response, dynamic response of the material. These are very important for design, for redesign, if you want to. The elastic modeling in all freedoms of movement. It can be used for material sorting. Is it acceptable or not? And for determining some sort of chemical compositions. But all these, the lower half of this, are specialized applications which require continuous development, which often require developments which are tuned to particular situations, particular material systems, particular type of damage. So it requires calibration at the back. And that is where a lot of research and development is necessary. And that is what we try to do at NML. And these often use techniques like magnetic hysteresis loop, magnetic Barkhausen noise, etc. But it often uses simple non-destructive ultrasonic techniques, maybe in a new avatar, a non-linear ultrasonics. So, ultrasonic is very popular. You can use longitudinal waves, shear transverse waves, or combined waves to probe a material. You have these phased array probes, which are essentially a piezoelectric probe which has been cut into small bits, which can be triggered and which can be used for receiving in different phases, different phasal configurations electronically. And through that, you can actually focus a beam, ultrasonic beam, and look at a particular area. You can also have a very large depth of focus and adjust each pulse to check various locations. You can also steer that focused beam to look at a sector, to find out where a defect is and what is the extent of damage. And it's not only defect, you can look at microstructural damage, you can look at the type of fatigue damage or creep damage that has taken place through these developments that are there in ultrasonics. And these are all available in the market, these sort of beam steering and beam focusing devices. You only have to use your software at the back or your concept at the back end in order to use, let's say, nonlinear. So I'll end over here. I think I've taken up quite a bit of time, 50 minutes. So I'm talking about damage and how it is incorporated. It has to be remembered. And how to non-destructively identify that damage and use that for making a decision if it is safe or if it is unsafe. If it has to be discarded or if it can be reused in terms of remanufacturing. So that is what we are trying to do. We must also remember that when you are talking about a system, there is always a weakest link. In your shoe, it's usually the shoelace that breaks from this location. That makes you unable to use your shoe in the first instance. That's because that is where the maximum amount of wear and tear damage is taking place. So using non-destructive techniques, using principles of structural integrity, you can always locate which is the weakest link and monitor that progressively, closely, in order to see if it is acceptable to use it, if it has to be discarded, if it is safe to continue to use it, if it can be used for remanufacturing, if it is structurally safe. So that type of thing. We also have to remember about the bathtub curve. Component or structure, there are early infant mortality failures which subside for a very long time throughout its life and far beyond. And there, of course, are wear out failures which may require repair, refurbishment if you have to continue. There are, of course, random failures about which we know nothing, accidents. And the observed failure rate is that. And it's all about the tools and techniques you have to counter the wear out failures, to understand this total failure scenario, so that you can pronounce if a component or structure is safe from the principles of structural integrity assessment, or if a component is reusable from a remanufacturing paradigm. So that's what I wanted to say. The demand on engineering structures is actually very fierce. You have high efficiency and increasing costs competing with each other. So we are going to continuously higher stress levels, higher pressures, higher temperatures, higher speeds, more severe environments. At the same time, we have to look for cheaper materials. We have to make the material stronger, therefore. We have to lower the section area. We have to lower the factors of safety. And we have to extend lives from the point of view of some of the sustainable development goals that we were talking about. So this is a tug of war, and we have to balance it very carefully. The failure often leads to very grave consequences. So this is what I wanted to convey. I hope I have been able to make my point. Thank you, and I'll be happy to respond to any clarifications that you will. Thank you very much.
Thank you very much, sir, for in-depth insight about the application of non-destructive evolution for integrity assessment, and you have very well explained about the repair steps and methods and uses, sir. We'll look for the question answer session. So I request to all the participants, if you have any questions, you can write your question in question answer box, or you may raise your hand. So anyone, if you want to ask question, you may raise your hand. I think one question is there, sir.
Yeah, I can see that from
Dr. Ultrasonic Poddar, yes, sir.
Oh no, I don't see that. I'm seeing only one in question and answer.
One question is there. So can I read, or you will?
Yeah, please read.
So the question is asked by Vasali Poddar. Is there any challenges in NDT for remanufacturing?
I think so. Yeah, I mean, NDT as a tool, as technology is pretty well developed. But it had been geared for a different applications in its development. It's only now when as remanufacturing is coming into vogue, that NDT is being directed to remanufacturing, the examination of the components during remanufacturing. And a lot of development has already taken place. Challenge is always there that can you use more advanced type of NDT tools for remanufacturing applications, use newer concepts. I presented a few, there are plenty more. And I think anyone who's trying to work in that area, who tries to look for the challenges, they'll find a lot of them. So the second question, if I can go on, is how can we detect volumetry defects in aerospace? Volumetric defects, you think?
Volumetric, yes, sir.
Yeah, I think it should be possible with NDT. I showed you what you can do with ultrasonics, and you can actually locate and determine the volume of the defect by scanning from various angles, from looking at the defect from various positions of the structure. Therefore, you know the boundary nearest to that location from where you are scanning and work out the volume through which the defect is there. There are processes that can be done, but of course, these are in the advanced design. Now, if you require a volumetric to find out a volumetric defect in the aerospace industry, I'm not very sure. Suppose you do sometimes, but not that important, I think. Okay. Then there is another question, ND for micro machining, micro manufacture, and additive manufacture products available. For additive manufactured products, no, really. This is one area where we are beginning to bite. Just some amount of research is taking place, but there are no standards, there are no procedures available yet in the open domain. People who are very deep into additive manufacturing, they might be having their own practice to follow, trying to use ND for gauging the quality of the additive manufactured product, but not really much in the open domain. And there is a lot of activity that is happening right now to develop such standards. Micro machining, micro manufacture, I suppose some standards are there because a lot of development has taken place, but I'm not the best person to answer that. Maybe Professor Mustafizur Rahman, if he is there, he was talking about some of those yesterday, and he would be able to answer. So moving on, there is best NDT equipment available for measuring depth of crack in complex cast product. I think ultrasonic. If it is within the body, if it is on the surface, then there are much simpler methods, dye penetrant and magnetic measurements, magnetic-based measurements that are available, magnetic particle measurement techniques that are available, but very standard products are available. Ultrasonic is the best one, but which particular equipment, brand of equipment, I would not like to state, or I would not even knowing perhaps, because there are so many brands available. Practicing NDT engineers would be able to tell. I am per se not an NDT engineer. I am more into R&D of structural integrity assessment. I've used such equipment, or my group has used such equipment. Some of the people in the group has better expertise in NDT, but we would not like to promote any brand if that is what you mean. So thank you very much. These are the questions that were there in the Q&A box.
One more question is, sir, Prakash Prasad. I just allow him. Prakash Prasad is there? Are you available there? Mr. Prakash Prasad. Okay, I think he's not there, sir.
Okay.
So thank you very much, sir. So on behalf of our organizing committee, that is NIMT and FAMFI, FOMFI, it's my privilege to present the vote of thanks on behalf of our organizing committee. We would like to express our gratitude to Honorable Speaker Dr. Soumitra Tarafdar, sir, who has spared his precious time for us and graced this sessions with his vital appearance and present a very enlightening presentation here in depth of NDT. Thank you very much, sir.
Thank you. Thank you for giving me the opportunity.
Thank you,
It's
sir.
good to see Professor Amitava Dey here. Looking forward to listening to you and Vishwakumar. Thank you.
We are going to move our next session. We have another two honorable speaker with us, Dr. Professor Amitava Dey sir and Mr. Sukumal Naskar sir. To continue these sessions, I would like to call my colleague Dr. Himanshu Khandewal. Sir.
Good afternoon, Professor Amitava Dey and all the panelists. So myself, Dr. Himanshu Khandelwal, assistant professor here in Foundry Technology Department. So on behalf of our organizing committee, Futuristic and Advanced Manufacturing Forum of India and National Institute of Advanced Manufacturing Technology, Ranchi, I welcome you, sir. And before I welcome you in the session of damage evaluation and build metal deposition. So before moving to a session, I would like to give a brief introduction about you, sir. So Professor Amitava Dey, he's a professor from IIT Bombay, and he has done his B degree from ISC Shivpur, West Bengal, and he has done his MTech and PhD from IIT Kharagpur, PhD in 1991 respectively. And later he has spent 2 years at the Institute of Joining and Coating Technology, Technical University Berlin, Germany, for 2 years under DART fellowship. He joined Indian Institute of Technology, Bombay, India as assistant professor in May 1998 and continued his career there and become associate professor, and now he's a professor. And his research area includes joining science and technology, additive manufacturing, and numerical process modeling. He has served in the several departmental and institute level committee as a convener and postgraduate academic performance committee from 2015 to 2017. He was also the dean academic program from March 2017 to 2021 at IIT Bombay. So he is regularly serving as the key and principal reviewer, associate editor, and editors for many of the key journals, broadly covering the metal joining and additive manufacturing area. So sir has more than 100 publications, high impact in high impact journal, and
That's not true. That's not true. I think we can stop. I think that is all. Let me start.
Okay, sir. With this, sir, I will like invite you. I'll send the session.
Okay. Let me share the screen. Yeah. Is my screen visible?
Yeah, visible, sir.
Lab bar is coming. All right. I hope I am audible too.
Yep.
Okay. But can you see my headings also or no?
Yes, sir. Your screen is visible, sir, and your voice is also very
Can you
clear.
also see the heading of the slides?
Yeah.
Okay.
Heading is slightly actually no.
Yeah. Do you know
Yeah,
how
now
to
it's
get
coming up, sir. Coming up. I think it was buffering. It is there, sir.
this black bar is? I don't know why it is coming. And the top. Anyway, I think we can skip forget that part. So good afternoon to all of you, the respected panelists and also the participants. I think we are almost in the lunch time, so I will try to be as brief as possible. And I I'm certainly thankful to the previous two speakers, and it's really, it takes a lot of courage, I think, to talk about this topic, especially after two eminent speakers like Professor Manna and Professor Tarubdar. I would require a lot of blessings, I'm sure of that. They are my seniors also in my college. So the topic I would like to talk now is metal additive manufacturing to reclaim damaged parts. And I must confess first that I wrote first the title as to remanufacture damaged parts. Then I realized that two times I will be talking of manufacturing on the title of the talk. So I just thought that it is a good idea to replace the word remanufacturing to reclaim, both meaning nearly the same in the context of what I will be talking now. And I am sincerely thankful to my PhD students like Prashant, Kajol, Pramod, and also my collaborators like Dr. Mukherjee, who is a postdoctoral fellow at Penn State, Professor Dweke, who is a faculty member at University in Germany, and Professor De Breuer at Penn State. So let me go into the topic. So as the title starts with metal additive manufacturing, I would like to give a short brief on what are the processes that we talk about. So as we all know that powder bed fusion with a laser heat source, directed energy deposition using a laser and powder. The powder comes along with through the laser beam, and directed energy deposition using a gas metal arc and a filler wire as the feedstock material are the kind of three major additive manufacturing processes that we are seeing these days for metallic materials, alloys. Broadly, we classify them, this particular process, as a powder bed process, where the bed of powder alloys are built or laid one layer by layer, and the laser works on that to finally melt and solidify in selected area to create a three-dimensional part, as we see here. In contrast, these two are kind of directed energy deposition process. I mean, I really don't know why the name has come like directed energy deposition. Perhaps the fact that the heat source and the feedstock material both come together and is directed to a local area to create a three-dimensional layer net shape is perhaps the genesis of the name of these processes, and especially the group as directed energy deposition. Broadly, if we try to look at their capabilities, this table from this particular reference gives us some ideas about what are the capabilities of these three broad processes. I have highlighted this particular two lines like rate of deposition of feedstock material. If we see that with powder bed fusion, the deposition rate is something around 25 to 180 centimeter cube per hour. This is based on the available literature in the openly available literature, published literature. In comparison to powder bed fusion, if you look at the directed energy deposition with a laser beam, it's much higher rate of deposition. And if we move to the gas metal arc based with a filler wire kind of process, we see the deposition rate is much higher. This is very important, as we'll come back to these values later. If we look at the bead size, typically powder bed fusion with a laser or electron beam, it builds so far based on the available information in the literature. We see that typical bead size of 800 by 400 by 500 millimeter are the highest maximum. In contrast, we have nearly 2 meter by 1.5 meter by 1 meter size of deposit or final part by a DED process with a laser, typically lanes, as some of us, I'm sure we are aware of that. And in gas metal arc based process, we see that the bead can go up to much higher size, like 5 meter by 3 meter by 1 meter, for example. course, there are other variables that are also very important to note, like we can have a much higher, or we will have a much higher cooling rate on a powder bed process because the bed pool is very small and usually it happens at a much higher scanning speed, if you notice here. Compared to that, the cooling rate at in GMA process, this process or welding this deposition process is much smaller because the pool sizes are bigger. So of course it takes time to cool. And there are other such different attributes of these three groups of three processes, which are important for building of parts. Now we are trying to talk about remanufacturing or reclaiming of a sort of perhaps damaged parts, and then we'll see how these things become more and more important. On the capabilities and challenges side, further, we see that these processes as a whole are capable of printing or fabricating very complex parts. That is the kind of prime novelty of these additive manufacturing or 3D printing processes. The part can have many geometric complexity. Of course, there are challenges like because of high stresses that are often generated as a part, as the parts are built layer by layer, there can be cracks. The part can be separated from the support, unwanted separation, which can lead to total failure of the part. It can be delaminated from the base plate because of high stresses, high local stresses generated. So these are some of the challenges which are already faced regularly by additive manufacturing processes. So it is not surprising that these situations will also prevail when we think of utilizing these processes for remanufacturing or repair. In summary, if we try to look at what type of processes should we go ahead, because we have to have some basis. Based on the available experience in the open literature, we see that powder bed fusion process is capable of manufacturing near net shapes with very little post-processing requirements. Very complex shape can be manufactured, okay, with a very good dimensional accuracy and surface quality. The product quality of PBF is observed to be much better than any of those DED-based processes, even when you compare them with laser-based DED process. But the problem comes when we start talking of high efficiency process. In particular, DED is proved to be much faster than PBF. Okay, and it's well suited for manufacturing of especially large structures because its deposition rate is much higher. That's what we can do. The material uses in DED is another big theme, another big saving that is in contrast to PBF process. The DED processes are, of course, found much more efficient. Okay? So we can use only the required amount of material because the filler oil is fed directly with the powder and it's fed locally. It's not like it's laid over a complete powder bed, and then it's always a concern how much of that powder we can reuse, and these are very costly feedstock material. So considering these two facts, that it can rebuild large structures faster and it is also efficient in use of materials, DED processes are kind of found much more appeal for refurbishing of existing parts. It's not really very surprising. That's where it started. Now let us go to remanufacturing or recreation. What is the kind of conceptual stage? We see that if we go for regular manufacturing, we use material, then we do some process and we get the final product. We use it and then it gets wear and tear in its service, and then at some point there is a decision whether this will go to incineration or we should go for a remanufacturing to save the energy, reduce the waste, and minimize the environment pollution. So this is a decision. Often it may not be at the hand of engineers at the management level, but imagine this is where the remanufacturing starts. So this is kind of life cycle of a part for manufacturing. Now, what's the value today? if we look at a typical scale in 2017, okay, this is from a review paper in 2017. If we see the output values of remanufacturing, in Japan, it's something around this, in UK, it's this, in USA, it's a much higher value. So it's not that remanufacturing is not happening, and these values are basically, as I said, from 2017, so it's already happening. And what are the processes? If you look at DED-based processes are almost doing 86% of the remanufacturing jobs in comparison to powder bed process or fused deposition mortar process. So they are having a much lower share. And which are the industries that are using this additive manufacturing, especially DED-based process for remanufacturing? If you again look at these turbine and new gas turbines, for example, they are using a major share of this. Of course, it is intuitive because things are much more costly, parts are much more costly there, and many parts are already made of some kind of very exclusive kind of process which are closely similar to additive manufacturing. So it is not surprising that this group of industries are already using remanufacturing to a large extent, followed by engines, railways, and die and tool manufacturing industry, and some other scattered area of industry. To go for a little more into that, what are the materials that are being used for remanufacturing? For example, we see that the materials that are being used are typically Ti-6-4, Inconel, stainless steel, even normal steel, okay, slight hard stained steel, for example, and of course stainless steel and tool steel kind of material. And these are some of the uses. Most importantly, we see, barring one or two cases, it's all DED-based process. So it's almost clear that this is the group of process, whether we use a laser or we use a arc welding based process, DED, directed energy deposition process, if at all being used for remanufacturing, this group of process will be supreme, or more or less, for using remanufacturing. And what are the challenges? One of the most important challenges out of many is the geometry complexity. I mean, where do we get stuck? We can decide that we go for 3D printing or DED-based process for remanufacturing, but these are the complexities. In most cases, if you see, the complexity is a geometric complexity. Okay? So the shape of the part that is to be reconstructed for reclamation of the part. Okay? Curved surface, overlaying the surface of a marine crankshaft, a hollow cylinder of gas turbine burner, which vary with varying thickness between 7.2 to 7.3, which means a very, very close tolerance. Overlay wearing on the surface of crankshaft, once again, a circular cross-section. So if we look at it, the geometric complexity is tremendous. Again, not surprising why DED-based processes are found more suitable for remanufacturing of parts if we consider additive manufacturing group for remanufacturing. Now, when I started studying what is this remanufacturing and how much is its penetration be. I casually looked at Web of Science, which is one of the most important database, as you know of. So when I give these topics and search how much publications are available in the open literature, we see not many. Why the above numbers are so small? When we know that in last 5 or 6 years, I mean, additive manufacturing is perhaps getting well over 50,000 papers perhaps published. So why not they are used for remanufacturing? Yes, there are reasons. Of course, I am sure that the numbers would be little more because many of the remanufacturing must be happening in a well-guarded secret manner within a certain industry, which are not published. But still, these are some benchmarks. Why? Let us look at some of the situations. This is the typical configuration of a gas metal arc-based directed energy deposition setup. Now, this is the torch, mid torch, and with so many cameras for monitoring. Okay, we'll talk about them a little later. But this is already known to be an effective solution for part repair because of its low material use, high deposition rate, and good structural quality. And as Professor Manna and Professor Tarokdar both have stressed upon, the knowledge of this group of additive manufacturing process is already there in the industry, in the engineering, research, and design teams, because they are coming basically from welding. So high deposition rates allow rapid manufacturing, and the filler wires is much more cheaper. So one of the reasons many times for reclamation of part will be cost, and this also serves very well with this process. Okay, now let us look at a typical example, a typical gray cast iron substrate which had a typical failure or wearing out area, worn out area, something like this. This is typically the cross slide of an instrument. And it was found that a typical nickel-based filler wire could be used to remanufacture this area, which was worn out, okay, after doing, of course, all the special procedures. And after some trial and error, it's found that a typical combination of process conditions are good to create a very well fill up, and the part is nearly reclaimed and put into use as before. And what are the situations that were observed? It was seen that with certain amount of current, voltage, and so on, certain amount of heat input, they have reported much lower porosities. When the heat input is increased, the porosities are much more. Not only this, further structural and property analysis was also done. Remember, the part was of gray cast iron, which is not very easy to handle, especially when you're talking of a repairing process that will involve localized melting and solidification. So people have taken due care. They have taken a very high nickel content based filler wire to take care of all those issues. And after some trial error, they must have finalized the actual process. And then this part was kind of initially machined, then with wire arc additive manufacturing, it was rebuilt, post-process, and finally it is remanufactured and it is completely in use once again, as it is reported in open literature. So after doing all the basic tests, property and structural characterizations. A typical damaged turbine blade of SS316A, again, this is an ideal component, ideal part for doing refabrication or repair, for example. Now here comes the difficulty. The right on the steps, the 4 steps, what you see here are the most difficult situations, because in an original building situation, there is a different geometry and path planning strategy, everything is different. Now, when we have to repair it, it's a completely different situation. The first very important task is to find out how much is to be deposited and how it is to be deposited. So this CAD geometry, the finding out what is the geometry that has to be deposited, what is the volume of material that has to be deposited, how it is to be deposited. Okay, so re-dimensioning of the whole thing, reconstruction of the geometry using solid modeling is the step number 1. That's the most difficult stage to begin with when we think of additive manufacturing or as a part for or as a process for remanufacturing or repairing or reconstruction of the damaged parts. But once this can be done, this is repaired, for example, by using a laser engineered net shaping type of process, which is a DVD process, laser based DVD process. And as you can see here, the parts could be repaired quite well, although there are certain issues. But of course, these require more and more process optimization. But what is more important here, that people have done some calculations and people have seen that it could be brought into the shape with some 18 layers of deposition resulting in total 45% carbon footprint improvement, 36% energy saving over replacement of a new blade. So I think in today's world, these are huge savings. This is also very, very economical, right? So the fact what I want to share with you is that this has a great potential, and we need to look at not only the process but also the geometry reconstruction, which also requires a tremendous attention because it is very, very difficult to start. Think of a defective gear, for example. The damage has happened to one of the teeth, for example. Once again, the steps remain the same. There is a tenacious reconstruction of the geometry to find out what should be the volume that has to be deposited and where it has to be deposited, how it has to be deposited. Once this is done, then if the process can be optimized, this same gear tooth can be once again refurbished, and after some machining, perhaps post-processing, this can be used as an original one. All right, so this can be done. So now let us see why therefore is the problem. Why can we not do this more and more into this remanufacturing process? And for this, we can go back once again to see what are the main challenges today for overall additive manufacturing processes, because they would remain the same. In fact, it would be more compounded because we are trying to build on already built material in a very, very localized region. So if we briefly look at, we see there are many challenges still unanswered in additive manufacturing or 3D printing, whatever we say. First, there are scientific challenges, how the microstructure changes, what are the relation between process, structure, and property and performance, because it will have layer by layer different cycles, thermal cycles, cooling rate, grain orientations during solidification, and morphology, and so on. Controlling it is not so easy. There are technological challenges. For example, how do we post-process? What are the roughness that we finally get? How much would be the dimensional consistency? Is there qualification and certification processes available? Are there already standardization? Because many components like turbine and other things, we cannot simply do it unless there is a standardization available, for example. And of course, there are economic challenges, cost, and other factors, feedstock material. As of date, for example, even if we talk of simple additive manufacturing processes, we know that only a few commercial alloys are reliably processed, not many. So this problem would remain consistent also for remanufacturing if we want to consider additive manufacturing as a potential route for remanufacturing of parts, worn out parts. So typically this is a very favorite slide of mine because I'm from manufacturing. So you know that this is an area which is always a problem for any new manufacturing process, that starting from demonstration and conceptual stage, can we scale up this? It's a huge difference. In a sense, we have a lot of processes now well established which can make these thin walls, even small part of the thin walls. But to scale it up, to repair a localized region here is a mammoth task. And to do it, I think it requires a huge amount of collaborative effort, a lot of study at a lot of places. Okay. And not only these trial and error studies, like in regular processes, we also require very fast responsive and reliable real-time monitoring techniques to know whether the process is happening correctly or not. Okay, because the processes happen very fast. So we need to monitor them. Now, if we look at that, okay, one of the method or traditional route that we have found out very useful in normal manufacturing, casting, forming, machining, simple welding, cladding, whatever we talk about. So far, we have seen that some kind of calculations or quantitative methods have always helped to get an idea, to get a better understanding of the process and optimize the process. Can we do this here also? And this is what is a huge challenge when we start with additive manufacturing. This picture shows, for example, the scale of the part compared to a normal, simply, if some of you are in the welding area, you will be knowing, or even forming. We are talking of not two simple plates bar welded side by side. We are talking of this kind of structure being built, or maybe part of it when it is repairing. The scale is havoc. So modeling this track by track, layer by layer, that means we are talking of something like 1 millimeter cube. If we want to think of modeling and seeing what is going to happen there, we are talking of 1 million cubic cells of 10 micron. And that might be for 1 million time steps or more, because that would be the size of localized melting and solidification in an additive manufacturing process. And these computational challenges have not been faced earlier, even considering laser beam welding. So there are many techniques which are coming up to sort of help additive manufacturing groups of processes, and I believe they would also help in grasping better ideas for remanufacturing by additive manufacturing processes, like microscale models, mesoscale model, multi-scale modeling approach. And some of these I can share with you, for example, like this. For example, models have been developed for getting an idea of what would be the shape of the bead, okay, in a typical layer by layer structure, typical thin layer wall structure in laser engineered net shaping process. It's a directed energy laser engineered net shaping process. So we see that the kind of model is able to predict what is going to be the shape of the part. And it shows that if we can do it better, perhaps we get a more uniform wall thickness. And if we can optimize this by the model itself, it can perhaps save a lot of trial and error tests with very costly powders. Not only that, these kind of models can also provide us very useful information. It can provide us information like layer by layer variation in the cooling rates. It can provide us an information of layer by layer variations in cell spacing, which can be correlated with variations in mechanical properties as we print the layers one after the other. And if these models can be verified with experimental results, they can predict things more reliably, and perhaps this can reduce a lot number of trial and error experimental studies. So this will help us not only in laser engineered net shaping process, even if we think of gas metal arc based directed energy deposition process like this one, right? In this case also, these models are now developed, which are well established. For example, to create layers by this kind of GMA process, and whether it is one track, one layer, three track, one layer, and these models can actually predict what would be the kind of shape of the profile of the deposit and how the temperature profile or melt pool or the track profile will be asymmetric as we move from one track to the neighboring tracks, which is intuitive, but we don't know how much it would be unless we do trial and error studies. So one alternative is this one, where we can reduce the number of trial and error much lesser. Okay. Not only that, these models can be used further, for example, to also compute the stresses, a very important factor to see whether the final build will have residual stresses. So we can predict or compute longitudinal stresses, we can predict transverse stresses across the layers, and this can provide us plenty of information. So these models can help us in optimizing the process by understanding a relation between process, structure, and property, which is one of the most important requirements for creating the process. And while I said that these models not only can be done numerically with a lot of computational infrastructure. It can also be done through analytical models. These models are also being developed to compute porosities and so on. As you can see here, these analytical models for typically PBF process, powder bed process, can predict the kind of porosity at different conditions. It can also predict the pool dimensions. So in effect, it can give us the track dimensions, whether it is unidirectional or bidirectional kind of scanning and so on. So now, if you see the result, when these models are now available, these models are now also used for rebuilding, for example. The same year before doing the actual process. Okay, in a subsequent work, these people also did a kind of model, thermal, to see what should be the track dimensions by which they have reduced the trial and error experiments nearly by half. As they have reported. Not only that, they have also been able to figure out what would be the expected stresses with the best possible scanning strategy. In a way, it is not only these models are providing a huge support, not only for conventional manufacturing, not only the way they have helped in understanding basic additive manufacturing processes, now they are also helping the additive manufacturing processes to come for repairing of parts. So a reason I told you why things are not going as high as normal additive manufacturing. Now with this, the models coming at the rescue of building or understanding the processes, I believe now these additive manufacturing processes will be much more available also for remanufacturing or repairing of parts. Ask remains monitoring. Just let us do a change of gear. So if we talk of monitor, what can we do for monitoring? For a typical GMA process that we use for this kind of directed energy deposition process. This is a typical current and voltage cycles, very complicated cycles, so that the heat input can remain as small as possible. That's all we can go ahead with this. Now, one way to do a monitoring of the process is to see how the arc is happening. We should not allow the arc to grow much bigger. So if we look at different steps throughout the arc of one cycle, we see that it's going on from a small to a large arc, melting, then immediately it's again a smaller arc, and this is a typical melt pool. This is the typical melt pool we are looking at longitudinally as the deposition is going on. Okay, so typically, if we see the unidirectional, for example, in a unidirectional scanning, it's going on in this manner. In a bidirectional scanning, we see the pool as it is depositing from right to left, it's having a much more uniform build pool. It's obvious because in a unidirectional kind of scanning strategy, it is already realized that if we try to do it, there will be a huge amount of build asymmetry because of distribution of asymmetric distribution of heat. In contrast, if we do a bidirectional scanning, there is an even distribution of heat through the length of the tracks, so it automatically becomes a much more easier deposition, okay, much more uniform kind of deposition. And how do we get it? This is how we do. So, this is how we did it. Here it comes. Okay, it's not coming. Okay, you can see it later. And not only from the side, we can also see the deposition from the top in a real time. And it shows us the temperature field, for example. As we look at it, as it moves on, we can look at through a camera how the thermal profile is coming at the top, which will give us an idea of what's going to be the melt pool from the top. Okay, and we can see for three different conditions like a lower heat input, a high heat input, a relatively moderate heat input with a high speed, how the melt pool on the surface is evolving. Not only that, during the deposition, it also shows as we go from the lower layers to the upper layer, how the melt pool can become asymmetric simply because of the fact, as we know, the melt pool is always kind of curvilinear shape in a typical way. So as we go from lower layer to upper layer, if we do not take due care, the molten metal can flow in one direction, right? So that would be kind of asymmetric. And if you see, if it is a fast freezing fluid, it will be more symmetric compared to a higher heat input condition. So this tells us that it is possible to do a similar kind of deposition with a monitoring strategy with a very uniform shape, which will eventually provide us a much more dimensional consistency during building of the process. Okay. So with this, I would like to stop with the few points as summary. Metal additive manufacturing is a promising tool for part reconstruction. Computer-based process models can provide a first concept to design and design to fabricate pathway and reduce cost against energy and feedstock. Current computational models demand for exceptionally high resource, so we may need to improve computational strategies and perhaps integration of mechanistic and machine language-based models to perhaps create or construct faster models, faster predictive models. And experimental investigations can generate a lot of knowledge base for process structure property relations. And we must be able to harness this information with these models to create better aim strategies. Thank you so much for listening to me. I will be happy to answer any questions if you have.
Thank you, sir. Thank you for your enlightening presentation. Now it's time for a question answer session. So I request all the panelists, if anyone has any question, they can post in question answer section and also in the chat box. They will also raise their hand so that I can allow them to speak. So I see there is, sir, there is one question here. That is from Mr. Rajnikant. Shall I read out, sir?
No, I can read. So can we quantify the geometric complexity of any part? So I think it is basically there are different ways you can do it, but I think it is more like the linear, curvilinear shapes, whether the shape is having any reentrant section. No? So this is the way we can quantify. But of course, it is very difficult to provide a single quantification measure. But I think the best way to say is how much is the nonlinearity in the geometry. That's the best way to represent it.
Yes, sir. So yeah, so there are a couple of more questions, sir.
I don't see any.
Yeah, so
okay,
you can.
I see.
Yeah.
Okay, this is a range as you see here. I already. So this would be typically, as of now, this is the reported results, from the literature. So of course, it is intuitive that in a directed energy process with arc and filler wire as the substrate, because it is having a slightly higher diameter compared to the powdered diameters, it will have a little smaller, little more rough surface. So post-processing is kind of required in this kind of process. In contrast, if we talk of powder bed fusion, where powder sizes are much more smaller, we will have a much better surface quality. So this is more or less known. But as of now, these are the kind of numbers that are reported in literature.
Yes, sir.
How we model the accuracy. I don't understand this question. Can you?
I think how
What do you mean by the accuracy?
how we model the
accuracy.
accuracy in direct. I think he.
So do you mean that how do you model DED process?
I believe so. There's someone from anonymous.
So I think basically the difference between DED and PDF process is to be, it is in the way you can consider in your model the, you know, the feedstock material. In one case, in DED, your feedstock material is coming through the heat source. So there would be certain amount of temperature of the feedstock material when it meets the made pool on the substrate or on the already solidified surface. In contrast, in a powder bed process, the powder is already laid on the bed. So the laser is directly irradiating on the powder. So that's one challenge to take care of. Second challenge, of course, is the scale. As I said, the more the size of the feedstock, the lesser the size of the feedstock material, the smaller the dimensions of the unit cells that you need for taking care of the local thermal history, for calculation of the local temperature field. What is happening there? What is the interaction between the source and the material? So to give you an idea, suppose you have a powder, a simple powder layer, a single powder alloy of 100 micron. Now to take care of the interaction of one powder particle with the laser beam, I mean, you need to have certain elements to account for the heat transfer, right? In contrast, when we have a larger filler wire diameter, which is under the arc, which is having a much higher diameter also as the source, of course, we can have slightly higher unit cell to account for the local thermal excursion. So that's how the computational demand increases as you go more towards the powder-based process. And often there are different schemes that are used to make the model scalable. Success of additive manufacturing without proper ND2, I don't agree to this. I think the more important is standardization. I think that's what you perhaps mean to say. See, there are most ND tools, as Professor Taladar has presented. I mean, the ND tools that are already available for most of the welding and casting can be used fairly without much exception. But the problem is standardization. And of course, the uncertainty of the layer by layer or track by track variations in process, structure, and property. That's the problem. ND tools are not the problem.
So thank you, sir.
Any other question?
Yeah, so these are the, I think, only questions, sir. If anyone has any other question, they can post. I see there is one hand raised by Nandita Gupta, Professor. I'll just allow him.
Yeah,
to
I
speak.
can't see that.
No, I need to, sir, in attendees. Yeah. Professor
Good
Nandita
morning,
Gupta.
sir. Good morning, sir. I am professor in NIAMT. Sir, I have a question like in remanufacturing and repair, the uncertainty and complexity are the main challenges. So whatever you have covered over here, sir, how do you correlate with this, that uncertainty and complexity comes in way, like delay and whatever the monetary investments are there and whatever the life later on being achieved are being influenced with it?
So I would like to answer this with the base on using this particular component. So now let us only imagine some numbers. So let's say if we want to talk about remanufacturing of this or reclamation of this, in contrast, in competition to rebuilding of a new blade totally, all right? So I think there would be a cost comparison. But now from the technology point of view, the reconstruction of this is also not a small aspect, because we have to take care of the existing structure.
Okay.
So if there is a local damage of the existing structure during building of this very specific amount of volume with a certain strategy, that's where the uncertainty comes from.
Okay.
So in other words, if we think of any kind of repairing, the difficulty or uncertainty comes from its future use, further use, right?
Yeah.
So whether that part can be really used, reusable or not, will depend on whether during this process, the initial structure could be, the property could be respected or not, could be, I mean, whether it will remain undamaged or not. That's the primary concern. Now, this is not known. This one can only do by trial and error study. Now, imagine a situation that for in developing a new part, people do pilot studies. Now, for doing this kind of test, you have no way to do a pilot study, right? This is only one-time situation. So it requires a lot of quantitative investigations to be confident enough to do.
Thank you, sir. Thank you, sir. It was a nice presentation.
Yeah. Thank you.
Thank you, sir. Thank you once again. So on behalf of our institute, I would like to present a vote of thanks to you,
Thank
sir.
you.
So thank you for sparing your valuable time and sharing your views on the metal additive manufacturing. And you have covered in detail, and you have also explained in detail how this DED, direct laser deposition, especially, and can be useful in the remanufacturing. So thank you for that.
Yeah.
So
Thank you.
now with this, I'll move to sir. You like to say?
Yeah. I'm not going to convey any special thanks to Dr. Rai, because whenever we wanted him to be with us, he has always agreed. And yes, the only one thing, remanufacturing is an area which is coming up. So all the presentations in this session are opening up the approach and perception to take up this new area. What I could figure out by this time is in between the conventional manufacturing and additive manufacturing. So that's a possibility, which is a new variant of manufacturing process. So we could look into that. Thank you. Thank you, Dr. Rai.
Yeah. So with this now, yeah. So with this now we'll move to the next speaker of this today's session. So we have with us Mr. Sukumar Naskar. So I would like to welcome Honorable Mr. Sukumar Naskar sir on behalf of our organization NIAMT and the Futuristic and Advanced Manufacturing Forum of India. So it's my indeed pleasure to present the a brief introduction of you, sir, before handing over the session to you.
I'll take 1 minute.
Yeah.
I mean, when we, like Dr. Soumitra Tarokdar, when we conceived the idea of remanufacturing, I mean, Dr. Sukumal Naskar was one of the person who helped me a lot. Earlier, he was in Siemens. Am I correct? So
Alstom.
Yeah, Alstom.
And Sandvik.
And were intimately engaged in welding and surface overlaying. Now he has switched to materials related to that area. So I believe he has the real potential to converge the use of material and its application to the process itself. So thank you, Shukamal, for agreeing with us and to present here with us. I know the kind of busy you are in traveling from one corner of the globe to other. So thank you very much.
No problem. Thank Can you allow me to make a presentation, because I think I need access.
Yeah. No, you have access, sir, already.
I have access.
Yeah, you have access.
Uh,
So
just
shall I take a 2 minute to introduce you, sir?
Yeah.
Or
yeah.
yeah, I'll just give a brief introduction. Already we have maybe 15-minute delayed the session. So yeah, so Mr. Sukumar Naksar, Naskar sir, he is the regional sales director, Asia Pacific Welding Alloys Services Private Limited, Singapore, and he's going to speak today on metal and alloys for regenerative manufacturing. So sir has did his BE from Mangal Engineering College in Metallurgical Engineering in 2004. He's the Master of Science in Welding Engineering from Canfield University, UK in 2021. Before that, he has also completed a Master's of Business Administration in 2015. He has a vast experience in the skill of welding, NDT, metallurgy, energy, pressure vessels, steel engineering, now related to the this remanufacturing field. So it's my proud privilege to have him today as the speaker of the session. So with this remarks, I'll hand over the session to you. Please proceed.
Thank you so much. Good afternoon to everyone. I think it's a very challenging time. Everybody must be very hungry. So I can see from the number of participants, it has already reduced like 21%. So thank you, first of all, NIAMT and FI, and thanks to Dr. Chattopadhyay, because, and I think know that he was my teacher during my undergraduate sessions. And thanks to all the renowned speakers in this event. I'm a little bit nervous because since the morning, so renowned speakers were there, and probably I'm one of the, I'd say, which is not so much related on the in details metallurgy, but I'll try to focus on something which is very in-depth in the industry. So the session is basically metal and alloys for regenerative manufacturing. It is a huge or vast subject, which I don't think in this 45 minutes time is impossible to finish. So when Dr. Chattopadhyay requested me, I decided to focus on only one industry, which is cement industry. So I'll talk mainly on the cement industry applications and solutions, and how we do basically remanufacturing or on repair and maintenance. So basically in the cement industry, if we see the entire process of producing the cement, every single process and components in daily life, we have to do the repair and maintenance or remanufacturing, because every single components are absolutely critical and every single components are very expensive. And if you think from the manufacturing, cement manufacturer point of view, a single day, if they stop their production due to any of these component breakdown, so it is a huge or immense loss for them. So in the current industry processes or standard, we used to do quite regularly or frequently different type of remanufacturing or repair and maintenance. It could start from the query. Let me see how it point. Yeah. So it starts from query, pre-homogenization, raw material, pyroprocessing, heating, and then silo, cement mill, clean, coal mill, preheating tower, everything, every single thing is associated with this repair and maintenance. So I'll go in details a little bit. So if we see this hard facing and repair solutions, we categorize like vertical roller mill, high pressure grinding and roller press, raw material crushers, clean or mill repair, pneumatic transport pipes, composite plate, and metal arc spring. I'll talk a little bit on this one as well. So first we'll talk about the VRM or vertical roller mill. So this is how it looks, the vertical roller mills in the industry. So there are different type of designers out there in the world. FLS is one of them, FLS Atox, OK, Lose is one of the very popular designer. So you can see that there are different types of vertical roller mills out there in the industry, which basically help on the cement industry. So, yeah, what we mentioned that we are doing hard facing in a VRM somewhere around the globe every single day in a year. 24/7 in 365 days. So here, schematically, it is showing that how it looks like. So here we have inlet chute, we have cage rotor, we have grinding table, we have nozzle, we have grinding roller, we have reject cone, and we have outlet dust. So these are some of the pictures where you can see that basically in the industry is a common practice to do the repair and rebuilding. Like this is basically cage rotor, this is basically the outlet chute and rejection cone. I'll show you in detail some of this. I try to make this presentation a more pictorial so that it can be easily understandable. So here it is a table. So what does this table do is basically, if you see this in this picture, so here is basically the table stage. These rollers is a giant rollers which continuously grind it roll and it grind the raw materials and make it fine. So these are the rollers. So these rollers are here, and this is basically table. So you can understand when you put the raw materials during fabrication of cement, it causes a huge effect of erosion and impact. So these tables is got very easily eroded. So each components are very expensive. So it is not possible that every time we can buy a new component. So what is the normal industry practice? We rebuild it to make it more usable condition for both the rollers as well as the tables. So here is a very good, you can probably visualize how big the roller could be. This is one of the rollers. So one roller, it could be like 15 to 20 feet in height. Okay, so this is basically how we do the roller repairs. Here, this is a good example. When you do this roller repair, we put the machine on top with this scaffolding, and we start doing this repair in the industry. So this is basically this is done. Basically, the previous one was done in the in situ condition, which was in the sites, and the next slide, which is basically in the workshop conditions. So we put it here, then we feed the machines, and it's automatically get repaired with a different type of machine components. Okay, so this is quite interesting, and this specifically I have taken this one from our UK. So what happened? I think we all know that during COVID-19, that's one of the toughest challenge we had, because most of the countries' border was locked, and the forging suppliers from India or China was unable to supply the forging to USA and in UK. So what happened that this became an interesting question, that like to be or not to be, that is the question. So it became the to scrap or not to scrap. That was the biggest question during this COVID. So we had one of the customers who actually invited us, and that these are the components which were lying in the scrap yard, and you can see it was badly damaged during this COVID. It was almost eaten up, and they requested us to visit their workshop and ask that because of the COVID, they're unable to source any of the raw materials and they cannot stop their production. So can we help them? So this is the component what we received. Like the question to scrap or not to scrap, it was actually scrapped. So we took this one from the scrap yard, and I told them we understood your situation, and you can see this is what we did a rebuilding. I think this is a very good example that remanufacturing or rebuilding has a huge scope. From the scrap, instead of making it scrap, we can reuse it. And this particular component is still running in the cement mill in UK. Okay, so how basically we select this is not a straightforward thing. We basically do is like a doctor. Okay, like example, we have a stomach ache. So the stomach ache could be in many reasons. So the doctor basically diagnose properly. We are basically a material doctor. So we try to understand the customer's required and need, and depending on, there are several solutions of one problem, but depending on the hardness level or how long they want to extend their life, we actually recommend them different type of solutions. Okay, so these are basically something which we basically focus, and how we focus is basically in this way. So we have abrasion, impact, metal abrasion, service temperature, corrosion. These are the 5 factors we take note, and depending on the applications, we grade this one, and then we basically recommend which is the most appropriate solutions. Okay, so this is another interesting solution. You can see here, these low rollers, whatever I just now mentioned, that it does not get eroded uniformly. So this is the area where it get the actual friction with the bed, and this area get much more eroded. So what we do is basically this inside we put it as a roll tire casting. Then we put basically another layer, which is this particular location is here, where it is not that much of wear is found. So we put mill 100 type, which is basically reducing the wear area. But this is the area where the maximum amount of wearing happened. So naturally, we have to protect that area more. So we use a high carbide type of solution so that it can really resist on the high wearing areas. And this is another layer which we put is basically shock absorbing ceramic metal complex composite. So this is a composite material which actually enhance the life of the roller. So here basically we did a little bit of experiment with the products, where depending on the customer requirement and amount of life and the tonnage of grinding operations what they do, it basically shown here. So this is how it basically looks. Is basically a real case study. So there are before we apply this mill curve hard facing, so it looks like this profile, and after we apply this one, it is showing in this way. And yeah, okay. So this is a quite interesting comparison basically, where you can see here that it was basically hard faced with the high chromium cast iron. So after 7,000 operating hours and after producing of 390k tons of cement, it looks in this way, where 10 to 30 millimeter of depression we can found. Then we apply basically a solution called mill curve, which is ceramic matrix, the composite hard facing. So after 7,000 hours and after producing of 390k tons, it is exactly same operating hours. You can see that only 2 to 4 millimeter heel area we have observed. Whereas this case, we have already observed 10 to 30 millimeter of erosion. Now the same component we further use in the operation, and after 19,000 hours with 1.06 million tons of production, we can still see that only 6 to 8 millimeter it has worn out. So we can see that depending on the requirement, or we can actually enhance the life of this kind of components. So this is exactly the thing. These are the rollers, which is basically they're all put in the scrap, and we actually took it back and we rebuild it, and we actually put it in the services. This is advanced grinding components, which are also used in the same way. We do a lot of hard facing. So we source and supply the new undersized casting and for pre-hard facing. So and then we made the proper hard facing as per the design of the original design of the mill, so that it can optimize the production of the cement. So here exactly same thing is called dam ring and nozzle. So it can be manufactured with a hard plate. What is hard plate is basically we put a special type of plate with a basically a hard facing layer of complex carbides, which enhance the life of these rings. The same thing. This is basically it's shown where this kind of things fit in the rotor blade. Okay. So these are all are used basically hard plate. So it is basically it enhances the life of these plates. Okay, it's a similar thing. It's called separator cone. So separator cones, because of the very high abrasion, it got eroded. So what we do inside and outside, we use a lot of hard facing to protect or enhance the life of these components. Next comes the high pressure grinding rolls. So there are several designs as well, like FLS Smith, KHD, Copran. So in this roller press is also goes under tremendous erosion and impact. So this is a quite interesting thing. You can see here that even we do a lot of hard facing, because of these hard components, sometimes it get basically impression. Once it get impressed, then it basically reduce the life of the component. So what we try to use is basically we designed a special type of complex carbides in the industry, so that we don't find any kind of cracking, no hard face spilling. So this is basically hard face spilling, no decrease in mill efficiency, and need to unscheduled repair. But these are the two most critical in the industry. If there is any kind of unscheduled repair, and that loss basically $1 million. So when in the industry we do this kind of repair, we make sure that there is no such unscheduled repairs happen. So this is basically a interesting product. Actually, it's our one of the patented product. You can see that it's very hard. It is showing crack, and that's not an issue because it's showing how hard is it. But the beauty is that this particular crack is restricted here. It does not penetrate inside the material, even after 6,400 working hours. So this is basically the RP. So this component, what is showing schematically, this is how this final component looks like. And you can find that different layer has a different metallurgical advance is there, and we basically use a different type of layers based on the applications. So this is what it's basically schematically look like. The core material is there. Then we have a hard face layer. Then first we have a build-up layer. Then you have a hard face layer. Then you put a pattern, and then there's a side protection is always there to basically help to protect the side wall of the rollers. So this is actually in the industry it looks like. So you can see that this is actually owned up, and we are basically doing the rebuilding. After we do the rebuilding, this component looks like this. So this is a quite interesting. You can see that how this roller looks like, and from there during this COVID, we just took this from scrapyard and we rebuild it, and it actually enhanced the life. And from the previous slide, as I show you that around 6,400 hours, it has increased the life here. So that's a tremendous amount of life has increased. Yeah, so this is basically in situ photo pictograph after using 20,000 hours, how it looks like. So we can see that we can use it. Okay, so exactly this is a very interesting where it worn out in the during operation. So we took it out, and after using we first grind it, we remove the old layer, then we start depositing, and this is basically how it looks like, the final component. Yeah, this is a schematically looks like. So this is how this roller actually works because of this high inlet and this erosion. So this basically the grinding zone. This is extraction zone, and this is centrifugal zone. So these are the areas we basically get eroded. Yeah, so this is basically shell hard facing we are doing here. So you can see this is a long torch we do, and then there's a method, and we do basically in situ repair in the cement plants. So practically we always get maximum 7 days shutdown. So we have to do everything we have to finish in 7 days. So we can understand how efficiently we have to put it. And next 1 year, the cement owners don't want any kind of unwanted stoppage of their production. So this is how it looks like after welding. You can see here. So next is basically raw material crusher. So there are different type of crushers out there: hammer crusher, blower crusher, roller crusher, cone crusher, jaw crusher, and all this crusher is basically they're crushing the raw materials to make the cement. And this is how it looks like. the cone basically get eroded, and these are the crushers. So it basically do the hard facing, and then we put it here. So this is how it looks basically. After operation on the crushing of the cement, the component looks like this, and then we start rebuilding. And you can see how. So this is the man of, let's say, 5 feet or 5.5, and this is one of the components. You can see how big it is. So this is another interesting component, which was, you can see, is almost was in a scrap, on the scrap yard in a hammer crusher, and then we took it back, and then it has been rebuilded and reused in the component. Okay, so this is basically the components where how it looks like, the bluebird crushers. And this is basically our 3D curve, which is our unique solution and patented product, to be honest with you. So this is the basically the crusher's hammer. We take it back, and then this is the layer we put. And you can see that we do not do like the complete welding in this way. We make a small squares, and it deposited so that it can enhance the life of the component. And this is a trademark product. It's our own developed technology in France. So this is a clinker or cooler crushers. So these crushers are basically here after operation, and then we start building the repair here. And this is how it looks after this repair and it's reused in the production. Okay. Next, I'll go to the clean and mill repair. So clean and mill repair is basically, you can see this is a clean type where it is very prominent that how much crack or worn out it happened. So basically these kind of components are very sensitive to cracking, so and it's very difficult to repair. So we have the know-how to repair this one, and basically we used it's called Gamma 182, is basically nickel based wire. So where this kind of thing we used to repair. So here, as I told you, that how we determine what kind of consumables need to do and what kind of things we need to take care. So it all depends on like here the corrosion was very strong, service temperature was quite high, the metal abrasion was quite high, impact was also moderate. So here this basically determines us to how to do or select the right compositions or the method to do this repair. So here it is a very interesting, you can see it was basically completely worn out, and we remove it and we rebuild it and we reuse it. Okay, so this was the actual picture of the component where from this crack we remove in this, and it is the amount of removal we had. And then from here we came here, we remove it, it excavate it, and then we rebuild it and we send it back for the operation. Next come pneumatic transport pipes. There are several transport pipes are there in the cement industry, where because of this cement it get quite erosion and corrosion, and then we do a lot of repairs of these components basically. So depending on the life, what the customer want, we have we recommend several type of products which could enhance the life of 6 times, 4 times, even 2 times. And with the maximum operating temperature also plays an important role. Composite plate. This is the one which are used almost everywhere in the cement industry. I just talked that this is called a hard plate, which basically enhance the life of the component by protecting from the all kind of erosion, sometimes even corrosion. So there are 3 types of hard plates are there: 100, 300, and 600. Depending on the application and the life enhance the customer want, we basically provide the solutions, and depending on the criticality. Okay, so that's one. So you can see here that we do basically testing of the STM G65 wire test, where these are mild steel, the wire life, then quench and tempered steel, then hard plate, 100, 300, and hard life. You can see that what I told, that depending on the customer's requirement or the amount of life they want, we recommend this one, the hard plates. and it's basically a complex carbides. So the micro hardness, how it goes, we think it's soft, but the moment it goes up to the fusion line, you can see it has drastically enhanced the hardness, like 67 to 68 HSC. So you can see that any kind of abrasion, impact, erosion, it can very nicely protect on the surface level. So yeah, exactly. So this is how it goes. This is the manufacturing technique, how you put it, and this is the final product, and it goes to the component. The last one, the metal arc spray. This is basically a new development for us. All previous one actually I shown is basically in the welding or fusion welding, but here the new technique we are developing basically. So it's called spray clad, is also registered trademark of us. Is basically arc spray process where two different type of wax are basically comes. It get melted, and with the force of air, we deposit on the surface of the component. So the beauty is that this spray clad coating does not affect the base material or form of and it is basically a form of mechanical bonding with a substrate of the hardness value between 970 to 2100 HB. The immense hardness basically we can create with a very thin layer. Sometimes the customer don't allow to deposit in a very high thickness like 2 millimeter, 3 millimeter, all these things. If customer basically need in a microns, so we basically use this spray cladding technique. And our goal is to provide the protective barrier of the substrate. Okay, this is basically very prominently used the solution of the spray cladding. Boiler panel cladding is a very good example, and you can see here that we have this is a boiler panel cladding, and this is a sealant applied. This is an anti-corrosion and erosion or abrasive layer, then bonding layer, and then prepare surface for the grid blasting. So this basically it helps or enhance the boiler life. I think we all know that boiler tube panel has a major problem is basically the panel get burst because of the high ash, or it get eroded from outside, and it become thin, and during operation it get burst. So because of this spray cladding, is a very fine in a micron surface coating we did it from outside, which actually protect the life of the boiler panel and actually enhance the life of the entire component. So I was trying to rush it because I know everybody is hungry. So that's all from my side. I have given my email address also here. If somebody has any questions after this session, please feel free to contact me. Thank you.
Thank you, Shukamal. I take the liberty to call you Shukamal because Shukamal is my fellow alumni from B College. In fact, from your presentation, you made us believe that remanufacturing is already implemented. It is already in practice. Actually, we do not have much to invent. Rather, we need to focus on the process of implementation, this particular knowledge as a technology. So usually we conclude such workshop with a valedictory session, but instead of that, we have a different plan. We have a forum, we call it Futuristic and Advanced Manufacturing Forum of India, where we have the members of advisory committee from different part of the globe who are very, very, renowned expert in manufacturing. So we will create a panel at FAMFI platform to review all these presentations and to come up with a foolproof roadmap for implementation of remanufacturing technology in one particular highly demanded area, right? So that is our approach in mind. So once we come up with that, we will again share with you the approach for continuation further. I convey my heartfelt thanks to all the speakers, to participants. More or less in all the sessions, we had around 100 participants. Although it is much less known area in our country, whenever I use this term remanufacturing, 90% people were under impression it is another version of conventional repair. So at least through these sessions and lectures, it is now established, in contrary to conventional repair, remanufacturing has to come up as a foolproof technology to pave the way for sustainable manufacturing, particularly in countries like India, which has a large economy, huge end-of-life products, and which is really a crisis and challenge for our economy. So thank you very much. We'll meet again. We'll share further.
Yeah,
Thank you. Yeah, before ending the session, I would like to again give a special thanks to our Honorable Director, Professor P.P. Chattopadhyay, sir, for his vision, encouragement, and dedication towards pursuing this particular area and this workshop. So thank you, sir, and thank you, and thank you all the guests, all the panelists, speakers, and all the participants. So with this, we'll end this today's session.
Okay. Thank you.
Thank you, sir. Thank you to Professor Mustafizur Rahman, who is basically the person who injected this idea in our mind. I mean, maybe 6 months earlier. So we didn't understand that, but gradually, as we pursued, now we are confident that this is an area of high-end technology. Thank you.
Thank you.
Thank you.
Thank you so much. Thank you for everything. Yeah.
Okay. Okay. Thank you, sir.
Thanks.
I'm happy.